Hello there, and welcome. Tonight, imagine lifting away from Earth as easily as an exhale, drifting toward the soft glow of a galaxy that appears as a faint blur to the naked eye. That blur is Andromeda, a vast realm of swirling stars and hidden energies. Inside it lie wonders that stretch imagination to its limit, from ancient remnants of devoured worlds to stars flung at impossible speeds. As we explore 100 awe-filled facts together, allow each one to settle gently, like starlight landing on water. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Chapter 1 begins in the quiet space between thought and imagination, where the vastness of Andromeda rises slowly like a lantern lifting through darkness. When you first picture it, you might see only a faint blur, suspended beyond the reach of the unaided eye, a soft smudge where sky and mystery blend together. But as you drift closer in your mind, that blur unfurls into a sprawling spiral more immense than anything our senses were built to grasp. Andromeda stretches across hundreds of thousands of light years, a wide river of starlight coiling through the dark, shaped by gravity and ancient motion. Its arms sweep outward in long, luminous arcs, layered with clouds so dense that within them, new suns are born in waves. To imagine its true scale is to let your awareness loosen, to give yourself permission to float in a space where distances cannot be measured in familiar terms. From afar, the galaxy seems serene, but its serenity is only the view from a great distance. Up close, its structure swirls with energy. The central region glows fiercely, a bright core wrapped in layers of stars moving in tightly curved paths. Astronomers call it a double nucleus, a kind of paired heart beating behind veils of dust. Each cluster of stars moves with its own rhythm, circling a massive dark anchor hidden at the center, shaping the inner light into a dense, shimmering knot. This region is brighter than entire smaller galaxies, yet if you stood close enough to witness it, the light would feel strangely diffuse, spread across an expanse so large that even brilliance softens into a golden haze. Moving outward from the core, the disk reveals its layered complexity. Andromeda's spiral arms are not delicate ribbons, though from a distance they might appear that way. They are thick currents of stars, gas, and shadowed dust, flowing around the galaxy like tides shaped over billions of years. Each arm carries clusters of blue-white stars, young and hot, blazing with the intensity of their short lives. Between them lie dark lanes of dust that trace sinuous paths, absorbing starlight and hiding vast structures behind their drifting silhouettes. Seen in infrared, these lanes glow softly, revealing reservoirs of cold gas waiting for the right pressure, the right nudge, to ignite into thousands of newborn suns. The galaxy's great sweep is anchored by its disk, a flattened but imperfect plane that stretches wider than two Milky Way disks laid side by side. In its inner regions, the disk seems orderly, shaped by steady rotation that draws stars into graceful circular paths. But farther out, the symmetry begins to loosen. The outer disk warps slightly, bending and twisting as if responding to a faint pull from unseen companions. This warp is subtle when viewed from inside, but unmistakable when seen from afar. A reminder that no galaxy is ever truly still. If you could drift above the disk and look down, the spiral pattern would appear both familiar and strange. The arms do not wrap around in perfect loops. They fork, split, reconnect, and fade, as if they were drawn by a hand that understood both order and chaos. Some regions flare brightly, crowded with active starbirth. Others grow dim, populated by older stars that shine with softer, steadier light. The entire structure resembles a dance frozen across unimaginable time, each star following its path not because it chooses to, but because gravity breathes through the galaxy like a persistent wind. Andromeda's luminous regions stretch far beyond what the naked eye perceives. Surrounding the bright disk lies a faint extended halo, a diffuse sphere of ancient stars scattered across enormous distances. Many of these stars belong to tidal remnants, lingering shreds of smaller galaxies consumed long ago. Their orbits form great loops and arcs, ghost-like trails that reveal a long history of encounters. Some of these features stretch for hundreds of thousands of light years, so faint they can only be traced by careful mapping. They remind us that Andromeda is not merely a static spiral suspended in silence. It is a survivor of countless collisions, shaped by the inflow of entire stellar families long since dissolved into its structure. The halo also carries globular clusters, tight globes of old stars that move like steady lanterns through the darkness. They orbit far from the galactic center, keeping to paths that rarely dip toward the disk. Their age, their chemical signatures, and their slow, measured motion all tell stories of a universe still young, long before spirals like Andromeda had settled into their current form. To picture them drifting across these vast outer regions is to understand that time in a galaxy unfolds differently, with eras lasting billions of years and change arriving slowly, like the turning of a distant tide. Closer to the disk, immense star-forming regions glow in arcs and swaths, illuminated by the radiation of young stars scattered within them. These nebulous clouds span dozens of light years and continually reshape themselves as gravity gathers material and stellar winds carve new cavities. In some of the brightest regions, you would see clusters of massive stars grouped so closely that their collective light bathes entire clouds in a gentle, luminous wash. In quieter stretches, dimmer clouds drift without awakening, holding their potential in silence until the conditions shift and new suns ignite. The structure of Andromeda's spiral arms is shaped not only by stars and gas, but by the invisible scaffolding of dark matter surrounding the galaxy. This unseen halo exerts a gravitational pull that keeps the outer regions rotating more quickly than expected. Without it, the arms would loosen and drift apart. Because of it, the galaxy maintains its sweeping form, a stable pattern held together by something that cannot be touched or seen. It is a reminder that galaxies, for all their radiant complexity, are guided by forces as mysterious as they are essential. As you drift through this chapter in your imagination, you might feel the scale of Andromeda begin to settle around you, not as something intimidating, but as something quietly astonishing. Its luminous arms, its hidden core, its layered regions of birth and decay, all joined together into a single structure that has taken billions of years to shape itself. Every star, every cloud, every sliver of light contributes to a portrait too large for any one perspective to capture fully. And yet, even from our distant vantage point, the galaxy reveals enough to remind us how vast the universe truly is, and how much beauty lies in the spaces beyond our sight. At the heart of Andromeda lies a region so dense and bright that it reshapes everything we imagine a galaxy's center to be. When viewed from afar, it appears as a single radiant knot, a glowing ember pressed into the fabric of the spiral. But as the view sharpens, the illusion dissolves, revealing not one core, but two, a pair of luminous clusters orbiting a common center like quiet companions locked in an ancient rhythm. One shines with a concentrated brilliance, packed tightly with stars that move in swift, curved paths. The other spreads its light more gently, elongated and uneven, as if it were once part of something larger that has since been stirred and pulled apart. Together they form a double nucleus, a rare structure that hints at a turbulent past. Surrounding these twin clusters is a swarm of stars so densely packed that they appear almost fluid, their motions layered and woven into one another. If you could stand suspended within that region, the sky would blaze on every side, filled with suns crowding the darkness. Their orbits twist and overlap, guided by a deep gravitational well hidden beneath the light. Near the very center lies a massive force, silent but commanding, shaping the entire region with its pull. Stars whip around it in tight loops, completing circuits in spans of time that feel impossibly short compared to the slow drift of the outer galaxy. Dust and gas thread through the central region like veils caught in a restless wind. These clouds obscure parts of the core from view, hiding pockets of intense activity behind curtains of shadow. In infrared light, the dust glows softly, revealing eddies and swirls sculpted by both gravity and radiation. Some clouds spiral inward, growing hotter as they fall toward the center, while others are pushed outward by the energetic breaths of young stars. The interplay of motion is constant, an intricate dance shaped by forces both visible and unseen. The double nucleus itself carries the memory of an earlier encounter. Astronomers believe it may be the remnant of a smaller galaxy long ago absorbed into Andromeda's center. Its stars now follow paths tilted slightly differently from the ones around them, moving in a pattern that hints at their foreign origin. Over time, the two clusters have settled into a strange harmony, circling one another while orbiting the deeper gravitational source at the core. Their combined light appears smooth from far away, but up close it flickers with the complexity of thousands of individual motions layered together. All around this nucleus, the central bulge rises like a soft, luminous hill made of countless overlapping stars. The bulge widens gradually, fading into the inner disk, but near the core it grows steep and brilliant. The stars within it are older on average, glowing with a warm golden hue that contrasts with the blue-white brightness of younger regions farther out. Their collective light reflects a long history of formation, collapse, and renewal, each generation of stars contributing to the slow shaping of the core. The environment around the nucleus is anything but peaceful. Stellar winds sweep through the crowded region, driven by the fierce radiation of massive stars that burn through their fuel quickly and end in spectacular explosions. These winds carve cavities in the surrounding gas, clearing pathways that reveal more of the inner structure. Supernova remnants expand outward, enriching the core with heavier elements that will one day become part of new stars and planets. The turbulence moves in waves, sometimes gentle, sometimes abrupt, but always present, always altering the landscape of light and shadow. Closer still, where the gravitational pull becomes nearly irresistible, matter spirals inward in thin streams. As gas falls toward the central mass, it heats to extreme temperatures, releasing bursts of high-energy light that ripple through the surrounding space. These flares come and go, evidence of brief feeding events that illuminate the unseen. Though Andromeda's core appears relatively quiet compared to the fury of distant active galaxies, it carries the unmistakable signs of past periods when it burned far more brightly. The double nucleus sits within this complex environment like a concealed engine, turning slowly through the dense glow. Its motion influences the stars around it, guiding some into elongated paths and capturing others in tight orbits that skim the core. The entire structure appears to rotate as a unit, though each component moves with its own distinct pattern. From above, the motion resembles a whirlpool with layered currents, each drifting in a slightly different direction, yet held together by the same deep center. As you drift in imagination through this region, you might expect chaos, but the impression that rises instead is one of slow, immense order. Even in the turbulence, there is a kind of rhythm, a vast coordination shaped by gravity's patient hand. The stars do not collide, though they pass incredibly close. The dust does not scatter aimlessly, but follows arcs and curves defined by the invisible contours of mass. The twin clusters continue their eternal circuit, never touching, never straying far, bound by a balance that has lasted for millions of years. The hidden core of Andromeda is not a single place or structure, but a layered world of light and gravity. Its double nucleus, its dense star clouds, its shifting gas, and its quiet central force all contribute to a portrait that is both serene and volatile. It is a region where time stretches differently, where stars live fast and motion is relentless, yet all of it unfolds with a grace that belies its complexity. To stare into this core, even in thought, is to glimpse a place where the galaxy keeps its oldest secrets, written not in words but in the turning of stars around a darkness that binds them all. When you drift outward from Andromeda's blazing core into the calmer glow that surrounds it, you enter a realm shaped not by the brightness of young stars, but by the quiet persistence of the old. These ancient suns are dimmer, cooler, and far more patient than their youthful counterparts. Yet they carry within their faint light a record of the galaxy's earliest chapters. To gaze upon them, even in imagination, is to look back across billions of years, past the spiral arms as they exist today, past the collisions that sculpted them, and into a young universe still learning how to form structure from its own expanding fire. Many of Andromeda's oldest stars reside in the extended halo that surrounds the disk, drifting in slow, elongated orbits far above and below the spiral plane. Their paths are stretched and tilted, crossing regions that younger stars rarely enter. These orbits are relics of ancient times, when Andromeda was still assembling itself, capturing smaller galaxies and merging with clouds of gas that carried their own primitive star populations. Each merger contributed new families of stars, some born elsewhere, some forged within Andromeda's growing mass, each carrying the chemical fingerprint of its origin. The oldest stars in this halo contain fewer heavy elements than almost any stars found in the disk. In astronomy, heavy elements are everything heavier than helium, forged in the cores of earlier generations of stars and scattered into space when those stars died. But in the early universe, before many cycles of death and rebirth had taken place, stars formed almost entirely from hydrogen and helium. The ancient stars of Andromeda preserve this scarcity. Their atmospheres hold only faint traces of metals, so faint that their existence offers a glimpse into eras before galaxies had fully organized themselves into spirals. These metal-poor stars shine with a subtle steadiness, their light softer and redder than the vibrant blue glow of young stellar clusters. Their longevity comes from their low mass, which allows them to burn their fuel slowly, stretching their lifetimes across spans of time nearly as long as the universe has existed. When you imagine one of these stars, picture a sun much smaller and dimmer than our own, glowing not with the urgency of youth, but with the quiet persistence of age. Some have endured for more than 10 billion years, long enough to witness the formation of galaxies, the birth of massive stars that have already lived and died, and the reshaping of Andromeda through mergers and collisions. Scattered among the halo are globular clusters, dense spheres of stars bound tightly by gravity. These clusters are among the oldest structures in the galaxy, predating most of Andromeda's disk. Their stars are packed so closely that if you stood inside one, the night sky would blaze with thousands of suns brighter than Venus appears from Earth. Yet even here, the age shows. Many stars in these clusters share the same low metal content, marking them as survivors from a distant era when the universe was still cooling from its primordial fire. Their shared composition suggests a common birth, a single ancient cloud that collapsed into a cluster long before Andromeda's spiral arms took shape. Closer to the disk, but still distinct from the younger populations, lies a group of stars known as the thick disk. These stars are older, hotter, and move in orbits slightly above and below the main plane of the galaxy. Their paths are more erratic, hinting that they may have been stirred by past interactions with smaller galaxies or formed during turbulent periods early in Andromeda's evolution. Their chemical signatures show more metals than the halo stars but fewer than the thin disk stars, placing them in an intermediate era where star formation had begun to recycle the heavy elements from earlier generations. The thin disk, by contrast, is home to the younger stars, bright and rich in metals forged over billions of years of cosmic recycling. Their abundance of heavy elements reveals a long history of supernova explosions that enriched the surrounding gas. But even here, among the young stars and active regions of formation, there are elders tucked away. Some stars in the thin disk may have migrated inward over time, shifting their orbits as the galaxy evolved. Their presence is like an old book misplaced among new ones. offering a quiet reminder that galaxies do not evolve in neat layers, but through constant motion and exchange. What makes these ancient stars so remarkable is not just their age, but the stories preserved in their chemistry. A star's composition acts like a fossil, recording the conditions of the gas from which it formed. Stars born early in the universe show almost no metals, because there had not yet been enough time for earlier stars to create and spread those elements. Stars born later contain more metals, their atmospheres shaped by countless generations of stellar birth and death. By studying these compositions, astronomers trace the lineage of Andromeda, reconstructing events that occurred billions of years before modern eyes looked toward the sky. Some stars in Andromeda are thought to be immigrants from galaxies long since absorbed. Their orbits and chemistry do not match the native populations, suggesting they were carried here during mergers so ancient that their original galaxies are now nothing more than faint streams of stars stretched across the halo. These stellar wanderers act as visitors from a forgotten era, their presence revealing that Andromeda grew not through gentle accumulation, but through the quiet dismantling of smaller systems drawn into its gravitational embrace. Every ancient star, whether drifting alone in the halo or bound within a globular cluster, offers a clue to the galaxy's earliest structure. Together, they form a mosaic of the past, a record of how Andromeda expanded from a modest collection of stars and gas into the sprawling spiral it is today. The fact that these stars still burn, still carry their pristine compositions, still follow paths carved billions of years ago, speaks to the immense timescales on which galaxies evolve. While human lifetimes measure only brief instants, these stars endure through cosmic epochs, witnessing events so slow and vast that they unfold beyond the reach of imagination. To wander among these ancient populations in thought is to touch the earliest memories of the galaxy. Their light is quiet but deep, shaped by a universe that was younger, hotter, and far more chaotic. They remind us that beneath the bright swirl of Andromeda's present-day beauty lies a foundation laid in epochs long vanished, held in place by stars that have watched the universe change around them without ever dimming their steady glow. Far beyond the luminous sweep of Andromeda's visible arms, past the stars that define its silhouette and the glowing dust that outlines its spiral, lies something far larger than the galaxy we think we see. It does not shine or cast shadows. It cannot be photographed in any wavelength of light. Yet it shapes the arc of every star, the curve of every arm, and the very rhythm of the galaxy's motion. This unseen presence is the dark matter halo, a vast sphere of invisible mass that surrounds Andromeda like a silent, weightless shell. Though it emits no glow, its influence is unmistakable. The galaxy orbits within it, suspended as if in the center of an immense, transparent sea. If you drifted outward from Andromeda's disk, leaving behind the bright lanes of starlight and the thin dust that drifts between them, you would find no sudden boundary where the galaxy ends. Instead, the light would slowly thin until only isolated stars remained, drifting like far scattered embers in the dark. But the gravitational pull you would feel would not fade as quickly as the starlight. It would remain strong, almost too strong for the visible matter alone to explain. This persistence is one of the first clues that something unseen surrounds the galaxy, extending far past what telescopes show. The stars in Andromeda's outer regions orbit much faster than expected. In a galaxy made only of the matter we can see, stars farther from the center would drift more slowly, their orbits stretching wide as gravity weakens with distance. Instead, the outer stars sweep around the galaxy with nearly the same speed as those closer to the center, defying the rules set by visible mass. This strange behavior is not unique to Andromeda. It is echoed across countless galaxies. But in Andromeda, so close and so well mapped, the deviation becomes especially vivid. The stars move as though gripped by a deeper mass, something that binds the galaxy together far more strongly than starlight suggests. This unseen mass forms the halo, a region so large that Andromeda's shining disk occupies only its inner heart. The halo stretches outward in a wide sphere, smooth and faint, with no edges we can touch or trace. Instead, we infer its shape from the motion of stars, the bending of light from distant galaxies, and the slow drifting of star clusters that would otherwise escape. These motions unveil a structure that is not rigid but gently curved, like a vast cocoon holding Andromeda within its grasp. Though we cannot see the halo directly, its footprint appears in every star that refuses to drift away into emptiness. Within this halo, small satellite galaxies orbit like distant companions. Some move in elongated paths, others in looping arcs that carry them above and below the plane of Andromeda's disk. Their motion is governed not only by the galaxy's visible mass, but by the far greater mass of the dark matter that surrounds it. Without this hidden halo, many of these satellites would have long since wandered off into intergalactic space, their orbits too slow to keep them tethered. Instead, they remain bound, moving through the halo like small fish circling a great shadowed current. Dark matter does not cluster into bright stars or glowing nebulae. It passes through itself and through ordinary matter almost without interaction. It cannot form planets, ignite into fusion, or collapse into the shining clouds that mark stellar nurseries, but its gravity sculpts the galaxy quietly from behind the curtain of visibility. It draws gas inward, helping the spiral arms maintain their shape. It governs the distribution of mass within the disk, influencing how stars are born and how long structures endure. It is the hidden architect of Andromeda's form, guiding its evolution through billions of years. Near the center of the halo, where the density is highest, dark matter deepens the gravitational well in which the galaxy spins. This well allows Andromeda to rotate as a nearly solid structure, its stars sweeping around the core in nearly synchronized motion. Without the halo, the spiral arms would unravel over time, flung outward by the momentum of their own rotation. But with the halo's gravity surrounding the disk, the arms hold their form. Patterns that might have dissolved remain intact, sustained by the quiet weight of the unseen. Dark matter also shapes the way Andromeda interacts with the galaxies around it. The gravitational bridge that stretches between Andromeda and the Milky Way is influenced not only by their visible stars, but by the enormous halos that surround them. These halos reach outward like invisible tides, overlapping slightly, tugging on each other across the intergalactic gulf. The future collision between the two galaxies is not driven solely by the glow of billions of suns, but by the deeper, darker mass that outweighs them many times over. In this way, dark matter does not merely bind Andromeda, it binds entire families of galaxies into loose clusters, their motions intertwined by gravity that originates beyond the reach of light. As you imagine drifting through this halo, you might expect emptiness, a void so complete that the idea of structure becomes meaningless. But the halo is not nothing. It is a field of gravitational presence, a silent architecture without walls or beams, but with form nonetheless. Its density is greatest at the center and fades gently outward, forming a profile so smooth that no visible galaxy could replicate it. In this intangible structure, Andromeda lives and moves. The stars do not see it, but they obey it. The mystery of dark matter remains one of the universe's most persistent questions. We feel its pull, map its influence, and build entire models of cosmic evolution upon it. Yet we cannot grasp what it is made of. Some theories suggest unknown particles drifting through space. Others propose more exotic explanations. But whatever dark matter proves to be, its presence in Andromeda is undeniable. It holds the galaxy together. It shapes the paths of stars. It controls the extent of the disk and the movement of the halo's outermost members. And in its silent embrace, Andromeda turns, luminous at the center, unseen at the edges, guided always by forces that have shaped the universe from its earliest breath. In the quiet reaches of Andromeda's spiral arms, long before a star ignites and long after its light fades, there are regions where creation lingers in a state of patient anticipation. These are the stellar nurseries, vast drifting clouds of gas and dust that glow faintly under the combined breath of nearby stars. From afar, they appear as dim smudges woven along the arms, but when the view draws closer, they reveal a landscape of swirling textures, luminous veils, and shadowed pockets where gravity begins its slow work. Within these clouds, the future of the galaxy gathers grain by grain, atom by atom, shaped by forces older than memory. These nurseries often stretch across distances so immense that a single cloud could cradle thousands of suns. Hydrogen forms their backbone, cold and dark, accompanied by dust grains that drift like soot in a cosmic breeze. For long stretches of time, these clouds drift quietly, disturbed only by the faint whisper of starlight or the soft pull of gravity tugging them into subtle folds. Their temperatures hover near the coldest limits of space, a chill so deep that molecules move sluggishly, allowing pockets of gas to condense with gentle persistence. This stillness is not emptiness, it is preparation. The process of star birth begins almost imperceptibly. Somewhere within the cloud, density builds just enough for gravity to tighten its grip. A small region grows slightly heavier than its surroundings, and as it draws more gas inward, it begins to collapse. At first, the collapse is slow, spread across a region far larger than any solar system. But as the material gathers, its fall accelerates, and the cloud begins to change shape. Filaments stretch and knot, forming long sinews of gas that converge towards central hubs. These filaments act like tributaries, channeling matter into growing cores where the foundation of a new star takes form. Inside these deepening pockets, pressure rises. Gas that once drifted serenely now swirls in spirals, its motion guided by the tug of gravity. As the core shrinks, its spin increases, flattening the surrounding material into a broad disk. This disk is the cradle of future planets, while the center becomes denser and hotter with every moment. Yet from the outside, the region still appears dark, hidden behind curtains of dust that absorb the light of early heating. Only in infrared can the faint glow be seen, a quiet signal that something new has begun to breathe. Stellar nurseries do not act alone in creating stars. Their evolution is shaped by the forces around them. A nearby supernova may send a shock wave racing through the cloud, compressing the gas and triggering a cascade of collapses. Stellar winds from young, massive stars can sculpt the edges of the cloud, pushing material into clumps that eventually ignite. Even the spiral arms themselves play a role, creating regions of higher density as they sweep through the disk. In this way, star birth becomes a rhythm influenced by the galaxy's motion, a cycle woven through Andromeda's structure like a heartbeat. When a core reaches a threshold of heat and pressure, fusion ignites. The transformation is instantaneous on a cosmic scale. A star that existed moments before only as a gathering of dust and gas suddenly blazes with light, pushing back the surrounding material with a burst of radiation. The energy carves out a cavity in the cloud, illuminating its walls with soft reflections. In clusters where many stars form at once, these cavities overlap, creating great sculpted hollows lit by the glow of newborn suns. The result is a scene of both delicacy and power, a balance between the destruction of the surrounding cloud and the creation of radiant new worlds. Within these nurseries, stars rarely form alone. They come in groups, sometimes hundreds or thousands bound together in loose associations. These young clusters drift through the cloud like pearls strung on invisible threads. Over time, most clusters will disperse, with each star following its own path through the galaxy. But in the early stages, the proximity of the stars influences their development. Their radiation shapes the surrounding gas, their gravity twists their paths, and their combined light turns the cloud into a softly glowing tapestry. Some regions within Andromeda contain particularly massive nurseries, places where oversized stars form in clusters so bright they can be seen across the galaxy. These giants live short lives, burning through their fuel in a fraction of the time allotted to smaller stars. Their light is fierce, their winds intense, and their presence profoundly shapes their environment. The shock waves they send through the surrounding gas can trigger new rounds of star formation, continuing the cycle even as they approach their own explosive ends. Their deaths seed the cloud with heavy elements, enriching the material that will form future suns and planets. Yet not all clouds within Andromeda produce stars. Some remain quiet, their density too low or their temperature too high to allow collapse. These dark reservoirs drift through the galaxy like unlit potential, carrying the ingredients of creation without yet receiving the spark. Over time, they may be stirred by passing waves in the disk, compressed by gravity, or illuminated by nearby events. Every cloud is part of the galaxy's ongoing conversation with itself, shaped by forces near and far, waiting for its moment to contribute to the tapestry of starlight. As you imagine wandering through a stellar nursery, picture drifting through soft curtains of dust lit from behind by pale reflections. Imagine clouds carved into great arches by stellar winds, filaments stretching across light years, and pockets of darkness where gravity holds its secrets close. In this environment, silence feels alive, filled with the slow gathering of material and the faint hum of energy rising toward ignition. The birth of a star is not a single event, but a long unfolding, a quiet shaping of the universe that proceeds with both patience and inevitability. These nurseries are the beating heart of Andromeda's evolution. They replenish the galaxy with new suns, renew the spiral arms with brilliant hues, and seed the future with planets that may one day host life. In their cold shadows and glowing pockets lie the beginnings of worlds yet unimagined. And although the processes within them span millions of years, each star that emerges becomes a new point of light in the vast river of the galaxy, a testament to the quiet artistry of creation woven into the fabric of Andromeda itself. In the long, quiet sweep of Andromeda's spiral arms, there are places where time feels layered, as though the galaxy remembers every bright beginning and every brilliant end. Among these memories lie the remnants of ancient supernova, the echoes of stars that once burned with a force capable of outshining the entire galaxy for a fleeting moment. Though the explosions themselves are long gone, the traces they left behind drift through the spiral in soft glowing shells, tangled filaments, and enriched clouds that now serve as the seeds for future generations of stars. To wander through Andromeda's supernova history is to walk through a gallery of cosmic transformation, each remnant a monument to both destruction and creation. A supernova begins quietly, deep within the heart of a massive star that has reached the final chapter of its life. For millions of years, that star fused lighter elements into heavier ones, building a core that eventually grew too heavy to support itself. When the balance between gravity and pressure breaks, collapse rushes inward with unimaginable force, followed by an outward burst so powerful that it hurls the outer layers into space at extraordinary speeds. From the outside, the explosion would bloom like a sudden sunrise, flooding nearby regions with intense light before fading back into darkness. What remains, long after the light has dimmed, is a shell of expanding gas threaded with the heavy elements forged in the star's core. In Andromeda, these remnants drift through the disk like delicate sculptures carved by energy. Some appear as vast rings of glowing gas, their edges lit by the heat of the blast. Others resemble tangled webs of filaments, thin strands shaped by shocks and turbulence. If you were to float within one of these structures, the gas around you would be so thin it would scarcely register. Yet from a distance, the entire cloud shines with a soft, colorful glow. The material spreads outward across hundreds of light years, gradually slowing as it mixes with the interstellar medium. Over time, the remnant becomes part of the larger river of gas and dust that weaves through the spiral arms, feeding the next generation of star-forming regions. Supernovae do not merely end stars, they enrich the galaxy. Within their cores, elements heavier than iron are forged in the final frantic moments of collapse, created under conditions so extreme that they cannot form in ordinary stellar interiors. These elements, once scattered into space, become part of the molecular clouds that collapse into new stars and planets. The calcium in bones, the iron in blood, and many of the elements that make planets solid were born in explosions like these. Andromeda carries these materials in great sweeps, distributing them through its arms in patterns shaped by ancient storms. Some remnants within Andromeda are relatively young, glowing brightly in visible and ultraviolet light. Their shock fronts expand into the surrounding gas, heating it to temperatures that produce soft, shimmering arcs. These arcs often appear asymmetric, influenced by the structures they encounter. A dense cloud might slow one side of the shell, while a lower density region allows the other side to race ahead. As the remnant evolves, its shape becomes a map of the environment it collided with, telling a story not only of the explosion but of the space into which it expanded. Other remnants are older, fainter, and more irregular. Their shapes have begun to dissolve into the fabric of the galaxy, their once defined edges replaced by diffuse wisps that blend with the background. Yet even in this quiet stage, they continue their work. Their material enriches the interstellar medium with heavy elements, allowing new generations of stars to begin life with a richer chemical palette than their predecessors. In this way, the history of supernova in Andromeda becomes a history of progression. Each generation of stars born with more material to build from than the last. In the halo above and below the disk, remnants of past explosions linger in near solitude. Massive stars are less common there, but those that once lived and died left faint bubbles of enriched gas drifting slowly through the thin outskirts of the galaxy. These bubbles expand with little resistance, forming wide, faint structures that require sensitive instruments to detect. Their presence reveals that star formation in Andromeda's halo was not always as quiet as it is now. Some of these distant explosions occurred when Andromeda was still young, still assembling itself through mergers and collisions that stirred gas into bursts of activity. The most dramatic remnants are those left by stars that were extraordinarily massive. These explosions send waves of energy through the surrounding medium, compressing nearby clouds and sometimes triggering the birth of new stars. In this way, the death of one star can awaken dozens of others, lighting up a region of the spiral like a string of lanterns. Andromeda's arms contain several such regions where clusters of young, bright stars trace the footprint of a long-vanished supernova. The pattern becomes a kind of cosmic rebirth, destruction followed by renewal. Some remnants hide neutron stars or even black holes at their centers. These compact objects, though small, hold incredible mass and exhibit powerful effects on their surroundings. A neutron star spinning rapidly sends pulses of radiation sweeping across space like a lighthouse in slow motion. A black hole may draw material inward, heating it to emit X-rays that pierce the surrounding darkness. These objects serve as lingering cores of the ancient explosions, silent reminders of the stars that once illuminated their regions. As you imagine drifting through Andromeda's supernova history, picture regions where the past is written in expanding rings of gas, soft ribbons of light bending through the spiral arms, and clouds enriched by heavy elements drifting toward star-forming nurseries. The galaxy breathes through these cycles. It receives the gifts of its dying stars, reshapes them into the foundations of new ones, and continues its evolution through rhythms that unfold over billions of years. Supernova history is not a story of endings. It is a story of transformation. Every remnant is a chapter in the ongoing creation of Andromeda, a moment when the galaxy reshaped itself through light, energy, and elemental richness. In their fading glow, we see not just the memory of stars that once were, but the beginnings of stars that have yet to be born. Far beyond the bright lanes of Andromeda's spiral arms, past the misty glow of star-forming clouds and the warm haze of the central bulge, there exists a quieter realm where time feels older and motion more deliberate. Here, the galaxy's most ancient families drift in slow orbits, bound to Andromeda, yet living in a world that feels separate from the luminous disk. These are the star clusters and globular groups, dense spheres of stellar elders that circle the galaxy like distant lanterns. They do not shine with the fierce brilliance of young clusters or the dramatic arcs of spiral arms. Instead, they glow with the subdued confidence of age, their stars tightly held together by gravity, forged in an era when the universe was still finding its structure. A globular cluster is a world unto itself. Its core is dense with stars, so tightly packed that the distances between them shrink to scales unimaginable from the calmer reaches of the disk. If you floated near the center of one, the sky would be a crowded field of light, filled with suns so close they would cast overlapping shadows across the surface of any imagined world. These stars are old, among the oldest in the galaxy, their compositions marked by a scarcity of heavy elements that reveals their birth in early cosmic cycles. They formed before the interstellar medium had been enriched by countless generations of supernova, which means their atmospheres hold the signature of a younger, simpler universe. Andromeda possesses many such clusters, scattered like pearls across the halo. They orbit far from the disk, following paths that stretch and curve over scales too vast to grasp intuitively. Some take hundreds of millions of years to complete a single revolution around the galaxy. Others move in tilted or elongated tracks, hinting at origins that do not fully align with Andromeda's early structure. These unusual orbits suggest that some clusters did not form within the galaxy at all. Instead, they may be the remnants of smaller galaxies long ago absorbed into Andromeda's halo, their star clusters surviving the merger even as their original hosts were dismantled and woven into the larger system. Within each globular cluster, the stars share a kinship that spans billions of years. They were born from the same cloud of gas, forged together in a burst of early star formation that produced a tightly bound group capable of surviving the tides and collisions that tear other stellar families apart. Unlike open clusters, which drift apart over time, globular clusters endure. Their gravity keeps them intact through encounters that would easily disrupt looser associations. This longevity makes them precious timekeepers. Their compositions and motions offer clues about Andromeda's past interactions and the conditions from which the galaxy grew. Yet globular clusters are not the only stellar families that populate Andromeda's outer regions. Open clusters, though younger and less tightly bound, inhabit the disk and spiral arms. They form within stellar nurseries and shine with the bright blue light of young stars. These clusters are more delicate, gradually dispersing as gravitational interactions and internal motion pull them apart. Over tens or hundreds of millions of years, their stars drift into the broader population of the disk, losing their group identity but carrying their origins within their chemical signatures. Andromeda contains many such clusters, some glowing brightly within the spiral arms, others already fading into the general background of starlight. The contrast between open clusters and globular families reveals the different phases of Andromeda's growth. The open clusters speak of ongoing creation, of regions where gas compresses into new suns that shine with eager energy before spreading into the larger galaxy. The globular clusters whisper of ancient epochs, of times when the universe was denser and star formation more intense. Their ages trace back to a period when Andromeda was accumulating mass through chaotic mergers and turbulent interactions. Some clusters show signs of having been pulled from dwarf galaxies that ventured too close. Their stars carry chemical patterns distinct from Andromeda's native populations, allowing astronomers to trace their origins like faint threads leading to long-vanished companions. As the clusters move through the halo, they feel the gravitational influence of the dark matter that surrounds the galaxy. Their slow orbits reveal the shape and extent of the invisible halo, providing one of the clearest maps of Andromeda's unseen mass. When clusters speed up or drift outward in ways that visible matter cannot fully explain, the presence of dark matter becomes unmistakable. In this way, the clusters not only record the galaxy's past, but help illuminate the structure that holds it together. Sometimes a cluster passes through the outer reaches of the disk, and during these encounters the dense tidal forces can peel away some of its stars. These wandering stars then stretch into faint streams that arc across the sky, subtle trails that trace the path of the cluster's journey. Over time, these streams blend into the halo, but for a while they remain as delicate reminders that even the most tightly bound families can be reshaped by the vast forces at work in the galaxy. Other clusters cling stubbornly to their compact form, resisting even the disruptive gravity of close encounters. Their resilience is part of what makes globular clusters such enduring features of galactic halos. They hold onto their members through epochs that witness the formation of spiral arms, the collision of galaxies, and the evolution of the universe itself. Through all these changes, they remain intact, their stars burning with quiet steadiness. If you imagine drifting alongside one of these ancient clusters, you might picture its stars glowing in warm hues, their light softened by age and distance. The silence around you would feel immense, broken only by the slow drift of the cluster as it moves along its orbit. Yet within that silence lies a deep sense of continuity. Each star is a witness to billions of years of cosmic motion, a survivor from an era when Andromeda was only beginning to take shape. The clusters speak in light rather than words, but their message is unmistakable. They tell of a galaxy built through time, through mergers and quiet accretion, through collisions that tore worlds apart and created new ones. They remind us that Andromeda is not simply the spiral we see today, but the sum of every star, every remnant, every family of light that has ever become part of it. In their orbits, in their chemistry, and in their enduring cohesion, the star clusters and globular families hold the memory of the galaxy's earliest breath. They drift far from the bustling disk, yet their presence shapes our understanding of the entire structure. And as they continue their slow paths through the halo, they carry the story of Andromeda's ancient growth, written in starlight that has endured across the ages. Far beyond the bright arms of Andromeda, past the warm glow of its disk, and into the cooler reaches of its halo, thin ribbons of stars drift like the remnants of forgotten rivers. They are faint, often impossible to see without careful mapping, yet they trace patterns that reveal a deeper truth about the galaxy. Andromeda is not a solitary creature that grew in quiet isolation. It is an assembly of many smaller worlds, each one drawn in by gravity, stretched apart, and woven into the larger tapestry. These tidal streams are the lingering footprints of galaxies that ventured too close and were gently, or sometimes violently, undone. What remains is the starlight they carried, smeared across the sky in arcs that wrap around Andromeda like ghostly trails. When a small galaxy approaches a massive one, the interaction is not immediate or explosive. It begins with subtle distortions, a slow tug as Andromeda's gravity reaches outward and pulls on the incoming system. Stars on the near side drift ahead, while those on the far side fall behind, stretching the smaller galaxy into a long, fragile strand. Over time, this strand becomes a stream, a structure that holds the memory of its former home, even as it dissolves into the halo. These streams continue to orbit Andromeda long after the core of the original galaxy has been consumed or shattered beyond recognition. Each one is a fragment of history suspended across millions of years. Some of these streams curve gracefully around Andromeda's outskirts, forming loops that can span tens of thousands of light years. Others fall inward, tracing more chaotic paths that hint at the turbulent forces that once shaped them. The stars within these streams are often older and more metal-poor than the stars of Andromeda's disk, reflecting the modest chemical histories of the dwarf galaxies they once belonged to. Their composition becomes a signature, an ancient fingerprint that reveals where they originated before becoming part of Andromeda's growing halo. If you were to drift beside one of these streams, the stars would not appear tightly packed. The ribbon might seem sparse, a gentle sprinkling of light across a vast darkness, yet their shared motion would tell a different story. These stars do not simply sit in place. They move together, orbiting in a way that marks them as siblings even after their original galaxy has been stretched beyond recognition. Their collective motion preserves the shape of the path they once followed, creating arcs and loops that map out the gravitational contours of Andromeda. Some of the most striking tidal streams in Andromeda were discovered only recently, revealed by precise measurements of stellar motion. Among them lies a giant stream that sweeps dramatically across the halo, a long, luminous scar from a collision that may have reshaped Andromeda's structure. This stream contains stars older than many found in the disk, stars stripped from a dwarf galaxy that likely plunged deep into Andromeda billions of years ago. The encounter flung them outward, scattering them into a structure that now circles the galaxy like the memory of a long-vanished companion. In other regions, smaller streams crisscross one another, evidence of multiple mergers layered over time. Each stream marks an event in Andromeda's long evolution, a moment when a smaller system was drawn inward and gradually dismantled. These interactions did more than redistribute stars. They also influenced the shape of the galaxy itself. The warp in the outer disk, the thickness of the halo, and even the subtle asymmetries in Andromeda's spiral structure may be the result of repeated mergers, each one leaving its own quiet imprint. The streams also reveal something about Andromeda's gravitational field. As the stars move along their stretched paths, their orbits trace the distribution of dark matter surrounding the galaxy, where the stream bends, where it widens or narrows, where it slows or accelerates. These variations reflect the gravitational landscape shaped by both visible and invisible mass. By mapping these motions, astronomers can infer the depth of the dark matter halo and how it extends far beyond the limits of the luminous disk. Yet the significance of these streams is not purely structural. They speak to the emotional history of Andromeda in a way that scientific language cannot fully capture. Each stream once belonged to a galaxy with its own stars, its own potential for worlds, perhaps even its own clusters and nebula. These smaller galaxies lived their own quiet lives before drifting too close to a larger neighbor. Their absorption into Andromeda was not an abrupt end, but a gradual unraveling, a kind of cosmic migration in which their stars found new orbits and new homes. Some became part of the halo. Some fell toward the disk. Some stretched outward into faint trailing arcs that remain visible long after the core dissolved. Through these streams, we witness the galaxy's appetite for growth. Andromeda is not simply expanding through quiet accumulation of gas. It grows by consuming companions, taking in their stars, their dark matter, and their orbital motion. Each merger reshapes the galaxy, deepening its gravitational field, altering the thickness of its disk, and leaving traces that persist for billions of years. The halo today carries the ruins of many such encounters, though only a few still appear as distinct streams. Most have already blended into the broader population of the halo, their stars indistinguishable from others except through their chemical signatures. If you let your mind wander through these faint ribbons of light, you might imagine drifting alongside stars that once belonged to a distant dwarf galaxy. You might picture their slow journey toward Andromeda, the gradual stretching of their home, the soft unraveling as gravity drew them apart. Their path now arcs across the galaxy in a silent curve, a reminder that Andromeda is not merely a single structure, but an accumulation of many lives, many histories, layered and intertwined. The tidal streams reveal the galaxy's past in threads of starlight. They show us where Andromeda has been, what it has consumed, and how it became the vast spiral that hangs above our night sky. Within their delicate patterns lies a map of ancient encounters, written not in ink or stone, but in stars that continue to move together long after their original world has faded. Through them, we glimpse a galaxy shaped by the very act of absorbing others, its beauty built from the remnants of smaller systems that once traveled independently through the darkness. Across the calm sweep of Andromeda's spiral arms, most stars drift along gentle paths, orbiting in rhythms that change only over millions of years. Their motion is steady, shaped by the mass of the galaxy and the quiet pull of countless unseen forces. But scattered among this orderly motion are rare wanderers that refuse to follow the usual rules. These are hypervelocity stars, objects hurled outward at such extraordinary speeds that they can break free from Andromeda's gravity entirely. Their journeys begin in chaos and end in solitude, carrying them far into the dark, where the galaxy's light fades behind them like a distant memory. A hypervelocity star is born in violence. These stars do not accelerate on their own, nor do they arise from gentle shifts in gravitational balance. Instead, they are flung outward by encounters that challenge the stability of even the most tightly bound systems. One of the most dramatic scenarios occurs near the central black hole, where gravity becomes fierce enough to tear apart stellar pairs. When a binary star wanders too close to the core, the immense gravitational field can seize one of the stars and draw it inward. The other is slingshot outward, launched with a speed so great that it escapes its former orbit and begins a long flight through the halo. If you imagine standing near such a disruptive event, you would feel the tidal forces twisting everything around you. The stars involved in these encounters are pulled and stretched as the black hole tugs at one member of the pair. For the companion star, the moment of ejection is both abrupt and decisive. It is sent outward like a stone cast from a sling, racing away from the core at speeds that dwarf anything seen elsewhere in the galaxy. Although the star itself remains intact, the path it follows from that moment onward is unlike any it would have taken under normal circumstances. Andromeda's hypervelocity stars do not always originate in the central regions. Some are created when clusters collide or when stars pass too close to massive objects that disrupt their orbits. Others emerge from three-body interactions, where complex gravitational interplay between multiple stars results in one being flung outward while the others fall into a tighter embrace. In every case, the ejection is a product of imbalance, a moment when forces briefly align to accelerate one star beyond the escape velocity of the galaxy. As these stars travel outward, they carry with them hints of their origins. Their composition often reflects whether they came from young regions or older populations. A star ejected from a cluster rich in heavy elements may still shine with the warm glow of youth, while one cast off from the halo might bear the chemical signature of much earlier star formation. Although outward motion erases their place within Andromeda's structure, the stars themselves remain a record of the environments that once shaped them. Their speed is their most distinguishing feature. A typical star in Andromeda follows a steady orbit, moving with the broader flow of the disk. A hypervelocity star races past these neighbors in a blur, its path not defined by rotation but by outward momentum. Some of these stars travel so quickly that they will eventually leave Andromeda behind, crossing its dark matter halo and venturing into intergalactic space. There, they will drift for billions of years, moving toward regions devoid of light, with no anchor to return them to their origin. These solitary travelers become nomads of the void, illuminated only by their own faint glow and the occasional distant reflection of cosmic background light. Yet while their journey seems lonely from a human perspective, the physics behind it reveals a profound connection to the galaxy's structure. The existence of hypervelocity stars is a reminder of the immense energies concentrated near the galactic core, where the central black hole governs motion with silent dominance. Andromeda's core is not simply a calm center, but a region capable of generating phenomena that reshape the fate of entire stellar systems. Every hypervelocity star that escapes its grasp marks another moment when the core's influence extended far beyond its immediate surroundings. These stars also provide subtle measures of the galaxy's gravitational reach. Their trajectories reveal how Andromeda's mass is distributed through its disk and halo. As the stars move outward, the rate at which they decelerate or maintain their speed reflects the strength of the gravitational pull acting upon them. If a star slows more than expected, it suggests a deeper reservoir of mass in the halo, likely in the form of dark matter. If it continues outward at high speed, the halo may be less dense than models predict. In this way, hypervelocity stars act as test particles, mapping the unseen structure that shapes the galaxy's outer boundary. Imagine drifting alongside one of these stars as it makes its slow departure. At first, the galaxy still fills much of the sky, a luminous whirl of arms and dust lanes. But as time passes, the spiral shrinks, becoming a glowing wound in the darkness, then a bright smudge, then a pale memory of where the star once belonged. Eventually, Andromeda becomes one point among many, indistinguishable from the distant galaxies scattered across the night. The star continues onward, a lone ember traveling through a cosmos with no destination, moved only by the ancient force that sent it outward. Hypervelocity stars are rare, but their rarity gives them power. They tell stories about the galaxy's center, about the interactions that tear apart binaries and disrupt stellar families, about the gravitational landscape that extends far beyond the shining disk. They reveal how energy flows through Andromeda, how chaos shapes its evolution, and how even a system as vast as a galaxy can cast off stars like sparks from a great fire. Each hypervelocity star is a moment of motion preserved across millions of years, a reminder that beneath Andromeda's graceful spiral lies a dynamic heart capable of eruptions and expulsions that send stars racing into eternity. Their journeys never loop back. They do not rejoin the spiral they once inhabited. They disappear into the dark, carrying with them the last whisper of the galaxy that gave them life. The great disk of Andromeda turns with a quiet determination, a motion so vast and slow that from any single point within it, the spin feels almost imperceptible. Yet the entire galaxy is caught in a continuous swirl, its stars orbiting the center in paths shaped by mass, both visible and unseen. If you could float high above the spiral and watch it unfold over spans longer than civilizations, you would see the arms shifting, the core brightening and dimming, and the outer regions sweeping through space like the slow unfurling of a cosmic tide. This rotation is not simply a gentle spin. It is a signature of forces that reach far beyond the starlight we see. Most of the stars in Andromeda move in nearly circular paths around the center, but the speeds at which they orbit defy the expectations of classical physics. In a system governed only by the gravity of what we can see, the outer stars should drift more slowly than those near the core. Instead, the stars on the outskirts move at nearly the same pace as those closer in. This unusual pattern is one of the clearest indications that something unseen fills the galaxy, adding mass that strengthens its gravitational pull. Without this hidden presence, the outer disk would not hold together. It would disperse like sparks blown from a fire. If you imagine riding alongside a star deep within the disk, the galaxy would not appear to spin around you. Your neighbors would drift at almost the same speed, creating the illusion of a still landscape. Only by comparing your motion to something far from your orbit could you sense the true rotation. The inner stars might appear to move slightly ahead, while those farther out lag just behind. Gradually, as ages pass, the spiral arms would shift position relative to your path, revealing themselves not as solid structures but as patterns that drift through the disk like waves through water. This rotation is not uniform. Near the center, where the mass is thick with stars, gas, and the pull of the central black hole, the orbits tighten and accelerate. Stars sweep around the core in far shorter cycles, each revolution marked by the deep gravitational well at the galaxy's heart. Farther out, where the visible mass thins, the speed remains unexpectedly high. This flat rotation curve has shaped astronomy for decades, prompting researchers to look for explanations that go beyond what telescopes can detect. The current understanding points to dark matter, a mass that neither shines nor reflects, yet exerts its influence across the galaxy. As Andromeda spins, its rotation affects more than just the paths of stars. It shapes the spiral arms themselves. These arms are not fixed lines etched into the galaxy. They are density waves, regions where matter piles up briefly as it moves through the disk. Picture a slow-moving traffic jam where the cars represent stars. The cars enter and exit the jam, yet the jam itself persists. In much the same way, stars drift into the spiral arms, linger for a time, and then glide onward, replaced by others following behind. This motion creates the graceful arcs that define Andromeda's appearance, curves lit by young stars born when gas clouds compress within the passing wave. Rotation also stirs the interstellar medium. Gas flows through the disk, shaped by pressure, temperature, and the motions of stars. As it orbits, The gas meets regions of higher density and shock fronts created by previous star formation. These encounters can compress the clouds, triggering new waves of creation. In this way, rotation becomes part of the cycle that births stars, seeds, clusters, and feeds the galaxy with fresh sources of light. The arms mark places where this cycle is most active, illuminated by newborn suns whose brilliance reveals the underlying structure. While the spiral arms move as patterns rather than fixed objects, the stars themselves follow a more individualized rhythm. Their orbits are not perfect circles. Many shift outward or inward over long spans of time, migrating through the disk in gentle drifts. This radial mixing smooths out the distribution of elements, blending the chemical signatures of different populations. A star born in a metal-rich region might slowly wander into an area where older stars dominate, carrying with it the memory of a different environment. Through this process, the disk becomes a patchwork, shaped by motion as much as by formation. The rotation also affects how Andromeda interacts with its surroundings. As it spins, it drags along its halo of dark matter, setting the stage for how smaller satellite galaxies orbit and how tidal streams stretch across the sky. The motion of the disk and the halo together creates the gravitational landscape that guides the paths of dwarf galaxies, some of which will eventually be drawn inward and torn apart. Their remnants will drift along new orbits, shaped in part by the rotation of the larger system that consumed them. If you were to drift above the halo and watch Andromeda's rotation unfold, the spiral would appear almost serene. The arms would sweep around the center in slow grandeur, their shape shifting subtly as star formation lights different regions and old stars fade from view. The disk would appear thin and luminous, bending slightly where the outer edges warp. Beneath this visible structure, the dark matter halo would expand like an invisible ocean, anchoring the motion and defining the boundary of the galaxy's reach. Yet even this vast rotation is not eternal. Over immense stretches of time, interactions with nearby galaxies, including the Milky Way, will alter the spin. The two galaxies are moving toward each other, pulled by mutual gravity along a path that will eventually lead to a merger. As they draw closer, their halos will interact first, sending ripples through their rotation. Later, their disks will distort, elongate, and twist. The rotation curves will change as the structures combine, creating a new galaxy whose spin will reflect the intertwined histories of both systems. For now, Andromeda continues its immense turn, a quiet motion that shapes everything within it. The stars orbit, the arms ripple, the halo binds it all together, and in the long sweep of cosmic time, its rotation becomes the pulse through which new generations of stars are born. Old ones drift outward, and the galaxy slowly transforms. The spin is not just movement, it is memory. It is the rhythm through which Andromeda becomes itself, age after age, turn after turn. Across the quiet dark that separates the Milky Way from Andromeda, there stretches a bond far older than human memory, a connection shaped by gravity, shared motion, and the slow drift of time. The two galaxies face each other across a gulf so wide it seems untouchable. Yet their relationship is intimate in ways that unfold only across millions of years. To look at them as isolated spirals is to miss the deeper truth that they are part of the same family, moving within the same small realm of the universe, responding to one another's pull with patient inevitability. If you could rise above the plane of the local group and look down on these two great spirals, you would see them not as static islands, but as travelers drifting toward each other. Andromeda leans slightly, its disk tilted relative to the Milky Way, while our own galaxy stretches outward in the opposite direction, each shaped by the complex dance of dark matter halos that encompass them. They are not moving quickly by human standards, but their motion is relentless. The space between them narrows with every passing moment, a slow contraction that began long before Earth formed and will continue long after its mountains and oceans have changed beyond recognition. This approaching motion did not begin recently. It is rooted in the shared environment from which both galaxies emerged. The earliest matter that formed the Milky Way and Andromeda likely condensed from the same primordial web of gas that filled the young universe. Before stars existed, before the first bursts of light illuminated the darkness, the seeds of both spirals were already threaded together by gravity. Over time, these seeds grew into the galaxies we know, each gathering its own clusters, its own stars, its own tides of dark matter. Though separated by enormous distance, they evolved within the same gravitational well, two siblings branching from a common origin. Even now, faint evidence hints at past encounters between them. Some models suggest that long ago, before either galaxy had taken on its modern form, they may have brushed past each other in a close approach that stirred their halos and ignited waves of star formation. Whether this ancient encounter truly occurred remains uncertain, but the possibility lingers in the motions of distant stars, in subtle distortions within their outskirts, and in the quiet shape of certain tidal structures that extend far beyond their luminous disks. If such an early meeting happened, it would mean that their bond began not merely in shared birth, but in shared disruption, a whisper of contact echoing across cosmic ages. Their relationship today is governed by gravity so vast that it draws both galaxies toward a meeting neither can avoid. The Milky Way and Andromeda move through the void with a kind of patient precision, guided not only by their visible matter but by the deep halos of dark matter that surround them. These halos stretch far beyond the edges of their stars, creating an unseen landscape in which their motions unfold. In some regions, the halos already overlap, forming a bridge of gravitational influence through which each galaxy subtly tugs at the other. The outermost stars feel this pull first. Their orbits shift slightly, bending in ways that reveal the quiet interaction happening on a scale too large to observe directly. As the galaxies draw closer, the space between them is filled with a kind of anticipation. Both spirals contain satellite galaxies whose motions hint at the future. Some of these smaller companions orbit in paths that seem shaped by the coming encounter, their positions reflecting the gradual tightening of the gravitational link. Others drift in elongated loops that will eventually bring them into the heart of the merger, where they will be torn apart and absorbed. Even now, before the true collision begins, the structure of the local group is bending in response to the approaching giants. If you were to drift in the darkness between the two galaxies, you would sense their motion not as speed but as a subtle shift in the sky. The Milky Way would brighten slightly over the ages as Andromeda approached, its faint shape growing more detailed, its spiral arms becoming distinct. The view would change so slowly that no single lifetime would detect it. Yet over millions of years, the transformation would be unmistakable. The faint smudge would swell into a glowing arc, then a vast whirl of stars stretching across the sky. Eventually, the disks would distort, their shapes drawn out into long, graceful streams of light. When they finally meet, the encounter will not be a collision of stars, but a blending of gravitational fields. The stars will mostly pass through each other, drifting like flocks of birds through overlapping air currents. But the overall structure of each galaxy will be profoundly altered. Their spirals will unravel, their cores will shift. Great tidal tails will sweep outward, carrying stars into enormous arcs that trace the violence of the interaction. Over time, the two will merge into a single, larger galaxy, a new system shaped by both lineages. The future descendants of Earth, if Earth still exists, will see a sky filled with complex light as the Milky Way transforms into something new. Yet even in imagining this future, it is clear that the relationship between these galaxies is not one of destruction, but of continuation. Their merger will not end their stories. It will rewrite them. The combined galaxy will carry the stars, clusters, and tidal streams of both parents, woven together into a new spiral, or perhaps an elliptical structure shaped by the details of the encounter. The memories of their past lives will remain in the motions of their oldest stars, in the chemical signatures of their clusters, and in the faint streams that trace the remnants of their earliest interactions. For now, the space between them remains wide, quiet, and deep, but the bond is already in motion, a slow convergence that began before the first animals walked on land and will continue long after all current landscapes are forgotten. The Milky Way and Andromeda move toward one another not by choice but by the fundamental architecture of the cosmos, drawn together by the same gravity that forms stars, sculpts galaxies, and shapes the universe itself. Their relationship is a story written across billions of years, a story of shared origin, gradual approach, and a future in which two great spirals become one. Far in the future, long after countless generations have come and gone, the night sky above whatever remains of Earth will begin to change. At first, the shift will be almost invisible, a faint widening of the soft smudge of light that marks Andromeda. Over spans of time too long for any single lifetime to witness, that distant glow will sharpen and grow, revealing its spiral arms in greater and greater detail, not with sudden brilliance, but with a slow, steady approach, like a lantern carried from across a valley. The Milky Way and Andromeda have been drifting toward each other since the earliest ages, pulled by a mutual gravity that binds them despite the enormous distance between their disks. Their merger is not a dramatic collision, but the quiet unfolding of forces long at work, a gradual convergence that will one day reshape both galaxies into something entirely new. In the early stages, long before the true encounter begins, their halos of dark matter will meet first. These halos are far larger than the luminous disks, extending in every direction like invisible oceans of mass. As they overlap, each galaxy will feel the subtle tug of the other's gravitational reach. Stars on the outer edges will shift their orbits slightly, adjusting to the combined pull. Satellite galaxies will begin to drift along new paths, some drawn inward toward the coming interaction. Still, to any observer within either galaxy, life will continue as though nothing has changed, the slow approach unfolding with such deliberation that it remains hidden within the pace of cosmic time. Eventually, Andromeda will loom large in the sky, stretching across a wide arc that dwarfs the familiar constellations. Its bright core will shimmer beside the dense band of the Milky Way, creating a sky filled with overlapping rivers of starlight. When the galaxies finally meet, the disks will not smash into each other like solid objects. Instead, they will pass through one another, their stars slipping quietly by without contact. Space is too vast, and stars too widely spaced, for direct collisions to be common. What will collide is the structure of the galaxies themselves. Gravity will twist their shapes, pulling long tidal tails outward in sweeping arcs that stretch across tens of thousands of light years. As Andromeda passes through the Milky Way for the first time, the sudden change in mass distribution will send waves rippling through both disks. Regions dense with gas will compress, triggering bursts of star formation that light up the merging structures with newborn brilliance. Though this sounds violent, the process unfolds slowly, more like the drifting of clouds than the clash of storms. Over millions of years, the galaxies will swing past each other, then begin to fall back together again, pulled by their combined gravity. The second approach will distort them even more deeply, elongating their cores and scattering stars into wide looping orbits. During these encounters, the central black holes of each galaxy will wander through the chaos, drawn gradually toward one another as frictional forces from surrounding stars slow their motion. Eventually, they will settle into a shared center, spiraling inward until they merge. This final meeting will release an enormous wave of energy, though by then, the surrounding stars will continue on their paths undisturbed. The new black hole will sit at the core of the merged galaxy, anchoring the structure that forms around it. The disks of both galaxies will lose their elegant spiral forms as the encounters continue. The delicate arms, shaped by their earlier rhythms of rotation and density waves, will unravel. Instead of sweeping curves, the galaxies will develop plumes, shells, and elongated structures that trace the gravitational tides, pulling them apart and stitching them back together. Stars born in the renewed bursts of formation will illuminate these features, creating glowing threads that link regions of gas and older stellar populations into complex patterns. Over time, the motion will settle. The The tidal tails will fade as their stars disperse into broader orbits. The once distinct shapes of the Milky Way and Andromeda will dissolve into a single vast entity, smoother and rounder than either spiral had been. This new galaxy may resemble an elliptical form, bright toward the center and gradually thinning outward into a diffuse halo. Star formation will slow as gas is consumed or heated, leaving behind long-lived stars that drift in slow, sweeping paths around the merged core. Though this future galaxy will look different from either of its predecessors, it will carry their histories within it. Some stars will trace orbits that once belonged to the Milky Way's inner disk. Others will come from Andromeda's outer arms. Clusters from both galaxies will inhabit the halo, their paths marked by ancient dynamics. Streams of stars pulled from satellite galaxies during the merger will remain as faint reminders of the complex interactions that shaped the final structure. From within, the night sky will reveal a transformed landscape. Instead of a single bright band marking the galactic plane, the heavens will be filled with a more uniform glow, stars scattered in every direction with greater density toward the core. The sense of belonging to a spiral will fade, replaced by the feeling of living inside a unified, luminous cloud of stars. The quiet arcs of the original galaxies will be gone, but the new structure will carry an impressive serenity of its own, a testament to the long journey that brought it into being. This future is not catastrophic. It is a continuation of the natural life cycle of galaxies, shaped by the same forces that formed them from smaller fragments billions of years earlier. The stars will continue to shine. Worlds, if they still exist, will continue their orbits. The merger will not tear apart planetary systems, except in rare cases where stars pass unusually close. Most of the cosmos will remain unaware that anything remarkable has happened at all. And yet, in the slow blending of these two spirals, there is something undeniably profound. The Milky Way and Andromeda are not simply drifting toward an end, they are moving toward a transformation, a moment when their separate stories will join into one. Their paths have been converging since long before life arose on Earth, and their union will shape the future of the local group for ages beyond imagination. The coming merger is not a collision, it is a meeting, a long-awaited union written into the structure of the universe itself. In the great sweep of Andromeda's spiral arms, where clouds of gas drift like luminous tides and newborn stars ignite with soft blue fire, countless worlds are forming in silence. They arise from the same timeless process that shaped the planets of our own solar system. Yet the details of their birth remain hidden behind the shimmer of distance. Andromeda, vast and ancient, carries within it not just stars but entire solar systems, each one a private stage where dust becomes rock, rock becomes land, and land may one day cradle oceans, weather, and something that breathes. To imagine planetary formation in a galaxy so enormous is to imagine billions of quiet beginnings happening at once, scattered across regions where light takes ages to arrive. The story begins within the dense molecular clouds that drift through Andromeda's arms. These clouds are cold and dark, filled with hydrogen, carbon compounds, and grains of dust left behind by older generations of stars. When gravity gathers enough material in one place, the cloud begins to collapse inward, forming a protostar surrounded by a rotating disk of leftover gas and particles. Within this swirling disk, dust grains collide gently, sticking together through static forces until they become clusters, then pebbles, then boulders. Over long stretches of time, these fragments continue to gather mass, growing into planetesimals that circle the young star in wide, glowing arcs. As the disk evolves, the interplay of heat, pressure, and orbital motion sculpts it into zones where different types of planets can form. Closer to the star, where temperatures run high, rocky worlds emerge from the densest material. Farther out, where frost can accumulate, giant planets collect thick layers of gas around solid cores. This pattern appears to repeat across Andromeda, echoing the process that shaped the solar system. Every star-forming region becomes the cradle of potential worlds, each one carrying the possibility of landscapes unlike anything we have known. Though we cannot observe these distant worlds directly with the clarity we have for planets in our own neighborhood, astronomers searching for exoplanets have found ways to uncover their presence through faint dimming of starlight or small rhythmic motions that betray the gravitational influence of orbiting bodies. Some of these signals come from stars within Andromeda's reach, subtle variations that travel across the gulf between our galaxies to tell us that planets exist in those far-off systems. These detections are rare and fragile, but they reveal that Andromeda hosts a menagerie of worlds as varied and complex as those discovered closer to home. Among the stars that populate Andromeda's spiral arms, many resemble the Sun in size and temperature, and these are prime candidates for hosting Earth-like planets. Their habitable zones are neither too hot nor too cold, offering environments where liquid water could exist. Around such stars, rocky planets may orbit with gentle regularity, bathed in light not unlike that which warms Earth's oceans. In other regions, red dwarfs dominate, smaller and dimmer but far more numerous. Around these stars, planets huddle close, receiving enough warmth to sustain temperate climates despite their proximity. Some might be tidally locked, presenting one hemisphere forever in daylight, while the other remains in perpetual night, creating worlds of extreme contrasts. Within Andromeda's vast interior also lie systems that defy the familiar patterns. Massive blue stars, short-lived but brilliant, may host young planets still wrapped in thick atmospheres of primordial gas. These worlds may never become stable homes for life, but they represent stages in the complex evolution of planetary systems. Farther from the disk, older stars, ancient red suns, enriched by the material left behind from supernova, carry planets with the heavy elements necessary for diverse geology. Iron, silicon, magnesium, and other materials forged in dying stars become the essential ingredients for solid surfaces and potential tectonic landscapes. Some exoplanet signals within Andromeda come from stars in tight binary systems, where planets must navigate the gravitational influence of two suns. These worlds may experience dramatic seasonal shifts as their stars trace paths across the sky in intertwined orbits. Andromeda likely contains trillions of such complex systems, each shaped by forces that differ subtly or dramatically from those that govern our own planetary history. Yet the most intriguing question is not just whether these worlds exist, but what they may become. In regions rich with heavy elements, planets might form thick atmospheres, oceans of liquid water, or surfaces carved by wind and volcanic fire. On planets orbiting older stars, where stability stretches across billions of years, life could take hold if the right conditions arise. It is tempting to imagine that somewhere within Andromeda, on a rocky world orbiting quietly between spiral lanes, chemistry has arranged itself into something that senses, moves, or dreams. Not because life is common or expected, but because the galaxy is ancient enough and diverse enough to allow for endless possibilities. Planetary formation in Andromeda is not confined to the spiral arms. Even the halo, sparse and faint, may host stars with lingering planetary systems formed in earlier eras. These worlds would be lonely, far from the energetic regions of the disk, orbiting in silence around ancient suns that burn with a quiet red glow. Their night skies would be filled with the faint light of distant stars, and the great disk of Andromeda would stretch across their horizons like a vast glowing river. Such planets would feel isolated in a way Earth never could. Yet they would remain part of the galaxy's broader story, drifting through the halo with slow, deliberate grace. As exoplanet searches expand, each new signal from Andromeda becomes a tiny thread connecting us to a system unimaginably far away. These signals speak of worlds forming everywhere, of planets that endure long after their stars settle into mature rhythms, of environments shaped by the same laws that shaped our own. They remind us that Andromeda is not merely a swirl of stars, but a cradle of untold worlds, each following its own trajectory through cosmic time. Somewhere within that vast spiral, a planet forms from drifting dust. Somewhere a world cools under the glow of its newborn sun, and somewhere, perhaps, a surface is waiting for the first quiet moment when chemistry becomes life. Across the vast breadth of Andromeda, where spiral arms sweep like great luminous rivers and dark lanes of dust curl in drifting patterns, there exists a framework that cannot be seen but shapes everything within its reach. Magnetic fields thread through the galaxy like quiet currents, twisting around clusters, weaving through star-forming clouds, and extending far into the halo. These fields are neither static nor uniform. They stretch, bend, and ripple in response to the motion of gas and stars, forming an invisible architecture that guides cosmic radiation, channels charged particles, and influences the evolution of entire regions. Though they cannot be captured by the eye, they leave traces everywhere, subtle signatures imprinted on the behavior of the galaxy. If you imagine moving through the disk of Andromeda, drifting among the stars and dust, you would feel nothing of these magnetic fields directly. They do not tug at objects with the familiarity of gravity. They do not glow or cast shadows. Yet they are present in the way charged particles spiral through space, in the shape of radio emissions, and in the gentle alignment of interstellar dust grains that rotate under their influence. These signs reveal a magnetic network that spans the galaxy, a system shaped by rotation, turbulence, and the flow of energy from stars both living and dead. The fields arise from the motion of ionized gas, stirred by the rotation of the disk and the turbulence created by supernova explosions. As the galaxy spins, the charged particles within it move in complex patterns, generating currents that strengthen and sustain the magnetic structure. The result is a field that wraps around the spiral arms, forming long threads that follow the shape of the disk. In regions of active star formation, where gas churns and massive stars inject energy into their surroundings, the magnetic field becomes tangled and compressed, creating pockets where its strength increases. These pockets influence how gas flows, shaping the density and structure of clouds that may one day collapse into new stars. Farther from the disk, the magnetic field becomes smoother, stretching into the halo where the density of matter drops and the turbulence quiets. Here, the field acts like a faint scaffold, guiding cosmic rays in long looping paths that wrap around the galaxy. These cosmic rays, high-energy particles born from supernova and energetic stellar winds, would scatter more freely without the magnetic field. Instead, they follow the curves of the invisible structure, sometimes trapped for long spans of time as they spiral around the lines of force. In doing so, they affect the temperature and chemistry of the interstellar medium, subtly altering the environment for future generations of stars. Cosmic radiation itself is an ancient traveler. It moves with astonishing energy, passing through gas clouds, dust, grains, and even the outer layers of stars. Within Andromeda, the intensity of this radiation varies from one region to another, shaped by both the distribution of supernova remnants and the magnetic pathways that carry the particles. Near regions of recent stellar death, the radiation is stronger, filled with energetic particles that have just been released into the galaxy. Over time, as these particles diffuse outward, the magnetic field steers them into patterns that reveal the structure of the field itself. The relationship between magnetic fields and gas clouds is particularly important in Andromeda's star-forming regions. When a cloud begins to collapse under gravity, the magnetic field can either resist or guide the collapse. If the field is strong and well-aligned, it can slow the inward motion of the gas, allowing the cloud to contract more gradually. If the field is weak or tangled, gravity can overwhelm it, pulling the material inward more quickly. The resulting star formation rates depend in part on this quiet interplay. In some regions, the magnetic field encourages the formation of long filamentary structures where stars form in chains. In others, it shapes the boundaries of large cavities carved by stellar winds, helping to define where new clusters will eventually arise. Within the spiral arms, where the field is stronger and more organized, cosmic rays spiral along the magnetic lines, illuminating the structure through radio emissions. These emissions, faint but measurable, trace the curves of the field in sweeping arcs. They reveal that Andromeda's magnetic structure echoes the pattern of its arms, following the gentle spiral outward until it reaches the quieter halo. There, the field extends into long loops and arcs, shaped by the galaxy's rotation and the faint turbulence that still stirs the thin gas on the outskirts. In the central regions of Andromeda, the magnetic fields grow more complex. The double nucleus, with its tightly packed stars and swirling gas, creates a turbulent environment where fields twist and break into chaotic patterns. These patterns influence how gas flows toward the central black hole, guiding streams of material along channels shaped as much by magnetism as by gravity. The result is a dynamic environment where energy flows outward in subtle ways, stirring the inner disk and affecting regions far beyond the core. Cosmic radiation in these inner zones is also more intense, enriched by the energetic processes surrounding the nucleus. Particles accelerated by magnetic turbulence near the core move outward, spiraling along the field lines in widening arcs. These particles help heat the surrounding medium and influence the chemistry of gas clouds drifting near the center. Though their paths are invisible, the energy they carry becomes part of the larger rhythm of the galaxy, feeding processes that echo through the entire disk. As you drift farther outward into the halo, the magnetic field gradually weakens, but it never disappears entirely. It stretches into great, faint structures that trace the galaxy's edges, influenced by the gentle pull of dark matter and the motions of satellite galaxies. Some tidal streams passing through the halo may follow paths subtly altered by the galactic magnetic field, their stars unaffected but their gas gently steered by the lines of force. These interactions are delicate but enduring, adding another layer of complexity to Andromeda's already intricate halo. If you were able to see these fields, the galaxy would appear wrapped in filaments of energy, glowing softly like threads of light woven through a tapestry of stars. You would see spiral patterns radiating outward from the core, arcs rising above the disk, and faint loops drifting into the halo. The magnetic network would reveal itself as both a product and a shaper of Andromeda's structure, responding to the movement of matter while guiding it in subtle ways. Andromeda's magnetic fields and cosmic radiation form an invisible heartbeat, a pulse that runs through the galaxy in silence. They shape clouds, guide particles, influence star formation, and reveal the unseen patterns that hold the galaxy together. They are the hidden architecture beneath the luminous spiral, the quiet framework through which energy flows and the future of stars is shaped. Throughout Andromeda's vast body, far beyond the bright swirl of stars and the calm lanes of dust, there moves a quieter, more persistent rhythm, the circulation of gas. This gas, often invisible, except in specialized wavelengths, is the true lifeblood of the galaxy. It travels upward from the disk in great fountains, drifts through the halo in slow currents, and eventually rains back down in wide, shimmering inflows that nourish new generations of stars. This cycle unfolds on scales so immense and over time so long that no single moment can capture it. Yet taken together, these motions form a breathing pattern that defines Andromeda's evolution. If you could hover just above one of the spiral arms, watching the flow of energy from clusters of young stars, you would see streams of gas rising like soft, luminous mist. Massive stars, in their fierce youth, heat the surrounding medium with winds that rush outward at astonishing speeds. Their radiation pushes dust grains and molecules into expanding shells, hollowing out great cavities within the arm. When these stars eventually die in supernova, they release bursts of energy that send shock waves through the surrounding environment. These combined forces lift gas from the disk, pushing it upward into the halo in broad, sweeping arcs. The process is gentle from afar, but within each rising plume, turbulence stirs like a quiet storm. As the gas ascends, it cools and spreads, losing the tight structures it held near the disk. In the halo, where densities are low and temperatures shift with the presence of cosmic radiation, the gas settles into wider streams. Some of these streams float in near equilibrium, suspended for spans of time longer than entire epochs of human history. Others drift outward until gravity gradually slows their ascent. A portion of this material may never return, carried so far into the halo that it becomes part of the galaxy's extended atmosphere, blending with older gas left from ancient mergers. But most of the lifted material eventually falls back toward the disk. When the gas cools enough, gravity reasserts itself, drawing the material downward in long, graceful inflows. These returning streams bring with them elements enriched by the lives and deaths of massive stars. Oxygen, carbon, nitrogen, and other heavy elements mix with the more pristine hydrogen of the halo, creating a blended medium that will feed future star-forming regions. This quiet rain of enriched gas ensures that each new generation of stars begins with materials shaped by those that came before. The inflows do not fall uniformly. Some return as diffuse veils drifting over wide regions of the disk. Others descend in narrow, focused streams that deliver concentrated bursts of material into specific arms. Where these streams meet the rotating gas of the disk, they create gentle shocks that compress the local medium, enhancing the likelihood of star formation. In this way, the gas cycle becomes part of the galaxy's regenerative process, feeding its luminous arms and sustaining the structures that define its shape. While fountains and inflows dominate the regions near active star formation, Andromeda also hosts long-range flows that move across the disk and spiral outward toward the halo. These flows are shaped by the galaxy's rotation, creating patterns that drift in spirals or arcs. They can transport gas from one region to another, evening out variations in density and carrying enriched material to places far from its origin. When a supernova goes off in one arm, the effects of its energy may influence gas hundreds of light years away, stirring turbulence that triggers waves of compression in distant regions. Such flows help explain how Andromeda maintains its ongoing star-forming activity. Without the movement of gas across the disk, certain regions would deplete their reservoirs and grow quiet. Instead, the galaxy's internal circulation keeps the medium replenished, ensuring that even older arms can birth new clusters long after the initial gas supply has been consumed. The quiet churning of the disk, barely perceptible on small timescales, allows Andromeda to sustain star formation over billions of years. Beyond the disk, the halo hosts another kind of gas entirely. This hot, ionized medium surrounds the galaxy like a faint, glowing shroud. Though extremely thin, the halo contains vast amounts of matter spread over an enormous volume. Gas from the disk feeds into this region, while cosmic inflows from the larger universe bring in fresh material. Streams from smaller satellite galaxies, pulled apart by Andromeda's gravity, add their own contributions to the halo's reservoir. Some of this gas eventually flows inward along cool, dense channels, reaching the disk and fueling periods of renewed star formation. These cosmic inflows come from the larger structure of the universe itself, remnants of ancient filaments that once fed the earliest galaxies. The interplay between outgoing fountains, incoming streams, and circulating flows forms a complex system that responds to the galaxy's internal forces. When star formation becomes particularly active in one region, the increased turbulence can drive stronger fountains, pushing more gas into the halo. This may reduce the local supply temporarily, slowing the formation of new stars. Later, when the inflows return, the cycle begins anew. In this way, the rhythm of gas circulation becomes self-regulating, preventing runaway activity and ensuring long-term balance. The cycle also shapes Andromeda's appearance. Regions with strong fountains may appear carved or hollowed, their gas thinned by upward motion. Areas receiving fresh inflows glow more brightly in ultraviolet and infrared light, revealing the mixing of materials and the birth of new stars. These variations add complexity to the spiral arms, creating subtle differences from one segment to another and giving the galaxy a texture that changes with time. If you could watch Andromeda from afar, across millions of years, you might see the disk pulsing gently as gas rises and falls. Spiral arms would shift in brightness as inflows ignite new waves of star formation. Great arcs of halo gas would drift around the edges, blending into the larger reservoir. The galaxy would seem to breathe, inhaling fresh material from the cosmos and exhaling enriched gas into its surroundings. This breathing sustains Andromeda. It feeds its stars, shapes its arms, and prepares the galaxy for future transformations. Through fountains, flows, and returning rains of matter, the galaxy continues its quiet evolution, guided by patterns too vast for any moment to capture, yet essential to the life of the spiral we see today. In the wide sweep of Andromeda's spiral, among regions where young blue suns ignite and older red giants drift in slow orbits, there exists a special class of stars whose lives unfold not with steady light, but with rhythmic brightening and dimming. These variable stars pulse like quiet beacons, their changes in brightness acting as a kind of language written across the galaxy. Though they appear subtle to the human eye, their patterns carry information that allows astronomers to measure distances, track motion, and map the structure of Andromeda with astonishing precision. They are not simply points of light. They are tools that reveal shape, scale, and depth, giving voice to the dimensions of the galaxy. The most well-known among these cosmic tools are the Cepheids. These stars expand and contract in cycles that repeat with remarkable regularity, each pulse revealing something fundamental about the star's intrinsic brightness. As the outer layers swell, the star cools and dims slightly. As they contract, the star brightens again. The length of each cycle is tied directly to the star's true luminosity, and this connection forms a bridge between appearance and reality. When astronomers measure the period of a Cepheid's pulse, they learn how bright it truly is. By comparing that intrinsic brightness to how bright the star appears from Earth, they can calculate the distance to the star with impressive accuracy. When Cepheids in Andromeda were first observed, their pulses became stepping stones across the void. Their measured periods allowed astronomers to determine that Andromeda was far beyond the boundaries of the Milky Way, a separate galaxy in its own right rather than a nearby cloud. This discovery reshaped humanity's understanding of the universe. A single class of stars, pulsing quietly in the distant spiral, revealed a truth larger than anyone had imagined: that the Milky Way was not the entire cosmos, but just one galaxy among many. In this sense, variable stars in Andromeda have been guiding lights not only through space, but through human thought, expanding the scale of the known universe with each carefully measured pulse. Within Andromeda's disk, Cepheids trace the structure of the spiral arms. Because they are young and massive, they tend to form in regions where star formation has recently occurred. By mapping their locations, astronomers can outline the bright, sweeping arcs of the galaxy. The distances derived from their pulse cycles help determine the thickness of the disk, the tilt of the spiral relative to Earth, and the precise separation between one arm and the next. Their light becomes a kind of blueprint, marking where new generations of stars are born and where gas clouds gather in dense lanes. Another important type of variable star found throughout Andromeda is the RR Lyrae class. These stars are older, smaller, and less massive than Cepheids, belonging to an ancient population that predates many of the spiral's younger features. They inhabit globular clusters and the halo, drifting in orbits that stretch far from the disk. Their pulses are shorter and their luminosity more uniform, making them excellent markers for tracing the shape and depth of Andromeda's oldest structures. By studying RR Lyrae stars, astronomers map the halo's extent and learn how ancient star families spread through the galaxy. RR Lyrae stars also help reveal the remnants of past mergers. When a dwarf galaxy is absorbed into Andromeda, its older stars often scatter into long tidal streams. These streams can be faint and difficult to detect, but RR Lyrae stars within them stand out like lanterns along an invisible path. Their pulses allow astronomers to identify which stars belong to the stream and which belong to the halo at large. In this way, variable stars become storytellers, preserving the memory of galaxies long since dissolved into Andromeda's gravitational field. Beyond these two well-known types are other variable stars that offer additional insights. Long-period variables, often red giants in late stages of evolution, swell and dim over spans measured in months or years. Their brightness changes reflect the complex processes within their vast outer layers. While they may not yield distance with the same precision as Cepheids, they reveal the distribution of older stellar populations in the disk and bulge. Some of these stars follow elliptical orbits that help trace the motion of the galaxy's deeper layers, offering clues about how Andromeda rotates and evolves over time. Eclipsing binaries provide another valuable tool. These systems consist of two stars orbiting one another in such a way that from Earth they periodically pass in front of each other. Each eclipse causes a dip in brightness that repeats with clock-like predictability. By measuring the timing and depth of these dips, astronomers can determine the sizes, masses, and orbital motions of the stars. When these systems exist in Andromeda, their geometry offers a second method of calculating distance. Though the technique is more intricate, it serves as a check against the results from Cepheids, strengthening the accuracy of Andromeda's measured scale. Variable stars also help scientists determine the galaxy's motion. As light travels across the void, its wavelength shifts depending on how quickly the source is moving toward or away from the observer. By analyzing the spectra of pulsating stars, astronomers can measure Andromeda's approach toward the Milky Way with remarkable precision. The faint shifts in the star's spectra, layered atop the rhythmic changes of the pulses, reveal the galaxy's slow inward drift. Each variable star becomes a probe of motion, a point of data that confirms the course of the future merger between the two spirals. If you imagine floating within Andromeda and watching these stars pulse, the effect would be subtle but mesmerizing. A Cepheid would brighten gently, reaching its peak like a calm breath drawn deeply, before dimming again in a steady exhale. An RR Lyrae would pulse more quickly, flickering in a pattern that whispers of ancient origins. Across the galaxy, these small rhythmic changes create an intricate network of signals, each one a voice speaking across space. Through these voices, astronomers map distance, trace motion, reveal structure, and study evolution. Variable stars become anchors in a sea of uncertainty, fixed points in a universe where most things change too slowly or too subtly to measure. They give Andromeda depth and dimension, turning what would otherwise be a distant swirl of light into a three-dimensional world whose contours can be charted with confidence. In their steady pulses, the galaxy speaks, and through their rhythms, we learn not only where Andromeda is, but what it has been and where it is going. Across Andromeda's luminous sweep, where spiral arms unwind like soft ribbons of starlight, there are stretches of darkness that break the pattern. They appear as shadowed threads woven through the disk, cold and silent in contrast to the warm glow around them. These dust lanes look almost like bruises on the galaxy's light, subtle from afar but immense up close. They obscure millions of stars, block entire regions from view, and hide structures that would otherwise reveal more of the galaxy's true complexity. Yet these darkened corridors are not empty or destructive. They are reservoirs of molecular material, the raw ingredients from which new stars will eventually form. And though they conceal much from our eyes, they offer astronomers a challenge that has shaped some of the most sophisticated tools in modern observation. When early telescopes captured faint images of Andromeda, observers noticed irregular dark markings cutting across its bright disk. At first, these shadows were misleading. They seemed to suggest that the galaxy contained voids or missing sections, as if something had carved out pieces of its structure. But as instruments improved, astronomers realized these patches were not holes at all, but clouds of dust thick enough to swallow starlight. Within these lanes, tiny particles of carbon, ice, and silicate float in dense concentrations, each grain small enough to pass unnoticed on its own. Yet by existing in vast collectives, These grains create curtains across the galaxy, absorbing visible light and turning entire regions opaque. Because our vision relies primarily on light in wavelengths that dust readily blocks, much of Andromeda's structure remains hidden when viewed this way. A spiral arm that appears faint or fractured may in truth be intact and thriving just behind a drifting dust cloud. Bright clusters can be softened into a diffuse glow, and the outlines of the galaxy's inner lanes can seem blurred or incomplete. Dust obscures truth as much as it shapes it, and while it plays a crucial role in star formation, its presence complicates the attempt to understand Andromeda's deepest layers. The dust itself is born from stars. When certain stars swell into giants and shed their outer shells, fragile grains condense in the cooling material. Supernova explosions produce more, scattering microscopic fragments into the interstellar medium. Over time, these particles gather into cold clouds, clinging to gas and accumulating mass. They drift slowly through the spiral arms, compressed by density waves and stirred by gravitational forces until they merge into vast, dark lanes. Inside these lanes, temperatures drop and light dims, creating pockets where future stars may begin their long journey toward ignition. Despite how much dust hides, astronomers have found ways to see through it, not by removing the darkness but by shifting their gaze. Dust blocks visible light, but it is transparent to longer wavelengths, like infrared. Telescopes designed to detect infrared radiation reveal structures invisible to the human eye. Behind the dust, star-forming regions glow softly, warmed by the heat of young suns still wrapped inside their birth clouds. Hidden clusters appear in places once thought barren. Entire extensions of spiral arms emerge, mapped not by starlight, but by the dust warmed gently from within. Infrared imagery transforms Andromeda. What appears broken in visible light becomes whole. What looks dim becomes bright. The galaxy reshapes itself, revealing an underlying structure more intricate than earlier astronomers ever imagined. This ability to see through the dust is not a simple one. It requires sensitive detectors cooled to extremely low temperatures, shielding them from interference, so faint signals can be captured. But without these tools, the true contours of Andromeda would remain half concealed, its story told in fragments rather than in full. Radio telescopes provide another way to pierce the dark lanes. While dust absorbs visible wavelengths, it allows radio waves to slip through unimpeded. By tuning into the natural emissions of hydrogen gas, astronomers can trace the distribution of material inside the obscured regions. This gas outlines the skeleton of the spiral arms and reveals the motion of clouds drifting within them. With radio observations, the hidden parts of the galaxy begin to move, showing how dust-laden regions rotate, stretch, and interact with surrounding structures. Even when starlight is swallowed, the motion of gas speaks clearly. There is also light from dust itself, faint and subtle though it may be. When exposed to the radiation of nearby stars, dust grains warm slightly and re-emit energy at longer wavelengths. When viewed with far infrared telescopes, these dark lanes glow with a delicate outline, not bright but unmistakably present. They appear like cold rivers threading through the hotter regions of the galaxy, carrying stories of material that will one day collapse into stars or drift apart into space. These dust lanes are more than obstacles. They are guardians of potential. Within them, the galaxy's future stars wait in embryonic calm. Dense pockets collapse under gravity, forming cores that will heat and brighten over millions of years. The dust shields these forming stars from harsh radiation, giving them space to grow. Without dust, star birth would be a far more delicate and unstable process. The darkness that hides is also the darkness that protects. Still, for observers on Earth, the dust lanes remain one of the greatest challenges in understanding Andromeda. They alter the way light reaches us, reddening some regions and dimming others. They distort the visual shape of the galaxy, making it difficult to determine where the arms are most active or where clusters are most abundant. Astronomers must fold in corrections for extinction, adjusting their measurements to account for light absorbed or scattered along the way. Every calculation carries a shadow of uncertainty, a reminder that even the brightest galaxy can hold secrets behind thin veils of darkness. Yet these veils give Andromeda a kind of depth that feels almost alive. No flat, perfect spiral stretches across the sky, but a layered world with bright foregrounds and shadowed interiors, with regions that glow gently and others that disappear entirely behind curtains of cold dust. When imagining drifting through the galaxy, you would pass from bright, open star fields into dim corridors where light fades and silence deepens. These transitions would shape the journey as much as the stars themselves. Dust lanes show that even galaxies have hidden chambers, places where light cannot pass and time feels slower. But with patience, and with instruments crafted to see beyond ordinary sight, these chambers reveal themselves. They remind us that darkness in the cosmos is not emptiness, but often the beginning of something waiting quietly to shine. Across Andromeda's vast disk, where spiral arms sweep outward in long, graceful curves, there are features that do not follow the usual rhythm of a spiral galaxy. They appear as faint arcs, ghostly shells, and subtle ripples etched into the starlight, each one a lingering scar from encounters that happened long before humans ever began searching the sky for meaning. These structures are not immediately obvious. Some lie so faintly against the halo that only deep imaging reveals them, while others blend into the background glow like old memories softened with time. Yet these remnants hold stories of disruption and transformation, the signatures of galaxies that once drifted too close and were slowly undone by Andromeda's pull. When astronomers first noticed these arcs of stars, they were almost mistaken for distortions in the images, small irregularities in the light. But the patterns were too deliberate, too smooth, and too large to be accidents. The arcs wrapped around Andromeda in curved layers, like ripples spreading across a pond after a stone has fallen in. Except here, the ripples were made not of water but of entire stellar populations. Their paths, shaped by gravitational tides acting over spans of time far beyond ordinary comprehension. Each shell spoke of a smaller galaxy that approached Andromeda, lingered in its gravitational embrace, and slowly came apart. Its stars scattered into arcs that loop around the larger spiral. These shells do not form all at once. As a smaller galaxy spirals inward, pulled gradually by Andromeda's gravity, its outer stars are stripped first. They move into elongated orbits that stretch around the host galaxy, creating the first faint arc. With each pass, more stars are pulled free, forming additional layers. Over time, these shells drift outward, spreading into the halo like echoes of the original encounter. Some arcs are nearly complete circles, while others arc only partially, shaped by the angle at which the smaller galaxy fell toward Andromeda. Together they form a record of motion, a layered history carved into the galaxy's outskirts. One of the most striking structures is a vast loop that arcs far beyond the visible disk, a pale ribbon of stars that almost seems to hover in space. It is the remnant of a dwarf galaxy that lost its coherence long ago, its stars now drifting in a pattern shaped not by their original home, but by the deep gravitational well of Andromeda. These stars are older and metal-poor, clues that the captured galaxy once lived a quiet, modest life before it wandered too close to a much larger neighbor. Now they move in a slow and graceful procession, tracing the path of their dissolution. Closer to the disk, faint shells bunch together, overlapping like the layers of a fragile blossom. They speak of another collision, one that likely unfolded when Andromeda was still young, its structure not yet fully settled. The stars in these inner shells shine brighter than those in the halo, suggesting that the galaxy they came from may have been richer, more structured, and more vibrant. Their arcs wrap around the core in a nearly symmetrical pattern, a frozen moment of motion that continues to evolve as the stars complete their long loops. Collisions between galaxies rarely resemble the abrupt impacts imagined by the human mind. They are slow, almost gentle in their unfolding, happening over spans so large that even ancient civilizations would see no change across all their history. When a dwarf galaxy approaches Andromeda, The first sign of disruption is a stretching, a long tidal pull that draws the outer stars into a trailing stream. These stars drift farther with every orbit, pulled into new paths that gradually lengthen and rise above the plane. Only after many such orbits does the smaller galaxy lose enough material to dissolve entirely, its core stretched thin until nothing remains but loose stars drifting in patterns shaped only by Andromeda's gravity. The shells and arcs are not static. They continue to move, though at a pace too slow for human eyes to detect. As they drift, their shapes soften, becoming more diffuse, eventually blending into the halo. Some shells are crisp and bright, meaning their merger is relatively recent. Others have blurred into faint wisps, their edges fading as the stars spread out and mix with the larger stellar population. The clarity of each structure becomes a measure of time, telling astronomers which collisions happened in the distant past and which ones unfolded in the more recent chapters of Andromeda's story. These remnants also reveal something deeper about the galaxy's evolution. Andromeda did not simply grow from isolated clouds of gas and dust. It built itself, piece by piece, through encounters with smaller galaxies that drifted into its path. Every shell and arc represents another step in that growth, another chapter of gathered material that added to its mass and shaped its form. The galaxy we see today is not a pristine spiral shaped entirely from within, but a composite built from countless interactions, each leaving behind faint signatures still visible in the halo. Even the shape of the disk carries hints of these ancient collisions. Slight warps and asymmetries trace the influence of past encounters, where the pull of an approaching galaxy nudged the disk upward or downward, creating bends that continue to ripple through the structure. The lopsided nature of Andromeda's halo, with clusters more abundant on one side than the other, also speaks to these long-vanished partners. The arcs and shells are not the only remnants. They are simply the ones we can see most clearly, the ones that reveal themselves against the dark. If you could drift close to one of these arcs, the experience would be quietly haunting. The stars would not cluster tightly the way they do in a dwarf galaxy or globular group, but would spread out like a thin, delicate flock, each one a survivor of a lost world drifting through a new home. There would be no sign of the galaxy that birthed them, no concentrated core, only a faint curvature to their distribution hinting at the shape they once held together. These stars would shine with quiet persistence, unaware that their current paths trace the memory of a collision that ended long before they were born. In these shells and arcs, Andromeda carries the echoes of galaxies it absorbed, long gone but still whispering through the shape of its light. Far beyond the bright arms of Andromeda, past the regions where spiral structure still holds its shape and the disk glows softly with the light of countless suns, there stretches a realm so diffuse and distant that it almost escapes imagination. This outer halo is neither empty nor silent, though at first glance it seems to vanish into darkness. It is a vast sphere of wandering stars, drifting clusters, ancient remnants, and faint tidal streams, all held loosely in Andromeda's gravitational embrace. Out here, the galaxy feels less like a structured city of stars and more like a quiet frontier where the boundaries between one world and the next begin to blur. The outskirts exist at a scale so large that outer stars require billions of years to complete a single orbit, moving at a pace so slow that their journeys resemble geological time more than celestial motion. These distant stars are old. Many were formed before Andromeda took on the spiral shape that defines it today. Their light carries traces of a universe still young, their atmospheres touched by the chemistry of a time when heavy elements were scarce and star formation happened in smaller, more fragile bursts. When astronomers study them, they find low metallicity signatures, evidence that these stars were present before the galaxy grew through its many mergers. Some likely belong to dwarf galaxies that have long since dissolved, their cores scattered across the halo and their individual histories folded into Andromeda's larger narrative. These halo stars are cosmic elders, bearing witness to epochs the disk cannot remember. Traveling inward from the outermost edge, The halo begins to thicken slightly, though the density remains nowhere near what is found in the disk or bulge. Still, faint structures appear against the dark, shaped by past encounters. Long arcs of stars weave across the halo like delicate threads, remnants of galaxies pulled apart by Andromeda's gravity. These arcs are not easily seen in visible light, but deep surveys reveal them as pale extensions curving far from the main body of the galaxy. They stretch across hundreds of thousands of light years, their stars moving slowly in elongated orbits that twist and stretch with each pass around the core. Many of the arcs intersect or overlap, a tangled map of ancient mergers. Globular clusters drift here as well, floating free of the disk like bright beads suspended in darkness. Each one is a dense concentration of hundreds of thousands of stars, bound together since the earliest eras of the cosmos. Some orbit high above the galaxy's plane, tracing long, looping paths through the halo. Others reside near the boundary where the disk's influence begins to fade. These clusters serve as markers, their motions revealing the shape of Andromeda's gravitational field. By measuring how quickly they move, astronomers can estimate the mass of the halo and uncover the presence of dark matter far beyond the luminous regions. When a cluster swings close to the galaxy, its trajectory shifts subtly, tugged by the unseen mass that extends well beyond the visible boundaries. The most distant stars in Andromeda's halo lie so far from the center that they exist in a domain where the galaxy's pull competes with the silent gravity of the intergalactic medium. These stars drift near the edges of Andromeda's influence, tracing fragile paths that may eventually lead them away into the emptiness between galaxies. Some of these stars are believed to have been ejected during past collisions, slung outward by gravitational interactions that reshaped their orbits. Others were likely captured from smaller galaxies that passed too close and left behind fragments of their populations. Out here, origins mix freely. The halo becomes a cosmological archive, layered with stars from many different families, each one carrying its own chemical story. At these distances, the galaxy appears as a faint glow behind you if you imagine drifting among the halo stars. The spiral arms blur into a soft haze, and the bright core becomes a distant ember. Around you, darkness stretches in all directions, broken only by isolated points of light. You might see a globular cluster shining like a suspended jewel, or a faint tidal stream arcing across the void. The silence would feel almost absolute, yet everything around you would still be in motion, moving slowly towards some future configuration shaped by gravity's patient influence. The halo also reveals something profound about Andromeda's mass. By tracking the velocities of these outer stars and clusters, astronomers discover that the visible matter in Andromeda cannot account for the speeds at which these distant objects travel. The halo stars move quickly enough that, without an enormous amount of unseen mass, they would drift into space and never return. Instead, they remain bound, connected to the galaxy by the vast dark matter halo that envelops everything. This halo extends far beyond the faintest visible stars, creating a gravitational domain much larger than the luminous disk. The outskirts, in this sense, act as test particles in a grand experiment, their motions revealing the shape of the invisible structure that defines the galaxy's true boundary. Within the halo, faint shells of stars can also be found, each one a relic of a past encounter. These shells form when a swallowed galaxy's stars settle into orbits that oscillate outward and inward, bunching together at certain distances before spreading thin again. Each shell marks the epicenter of these oscillations, a location where stars slow briefly before falling back toward the center. Over time, the shells drift apart, becoming thinner and more diffuse, but their presence persists for billions of years. They curve around the galaxy like pale echoes, almost ghost-like in their subtlety. One could wander among them without ever realizing their full shape, but when seen from afar, their arcs reveal the outlines of long-finished events. The outer halo is also a place where the boundary between Andromeda and the rest of the universe becomes ambiguous. The local group, the small collection of galaxies to which both Andromeda and the Milky Way belong, exerts a collective gravitational pull that shapes the motions of stars in the farthest reaches. Some of these stars feel a tug, not only from Andromeda, but also from the broader gravitational tide of the group. Their orbits become slightly distorted, influenced by forces from beyond the galaxy's immediate sphere. These faint shifts hint at Andromeda's place within a much larger environment, reminding us that no galaxy exists in isolation. In these outskirts, distances become vast, motion becomes slow, and time stretches toward scales that defy ordinary intuition. Yet even here, in regions where light is scarce and structure becomes faint, Andromeda continues to tell its story. Every wandering star and drifting cluster offers a clue to where the galaxy has been, what it has consumed, and how it has evolved. The halo may appear quiet, but it is filled with memory, written in the long arcs of orbits traced over ages. And from this distant frontier, the galaxy's grandeur becomes clear, its luminous core and sweeping arms held together by forces seen and unseen, shining across the void. Across the wide face of Andromeda, far beyond what ordinary starlight reveals, a deeper language flows through the galaxy, written not in visible brilliance but in waves and rays that the human eye cannot sense. These signals whisper through space in long, gentle arcs of radio, in the heated shimmer of infrared, in the sharp electric flare of ultraviolet, and in the fierce blue glow of X-rays. Together they form a spectrum of hidden voices, each one offering a different way of seeing the galaxy. Andromeda is not a quiet swirl of light when viewed with these senses. It becomes a place of motion, heat, turbulence, and ancient energy, a layered world where each wavelength uncovers something the others miss. Invisible light, dust clouds cast shadows, star-forming regions hide behind thick curtains, and the bright core diffuses into a soft haze. But infrared vision slips through places where ordinary light falters. When astronomers peer at Andromeda in infrared wavelengths, the dark lanes glow with warmth from dust, grains absorbing and re-emitting starlight. Structures that looked broken now appear whole, and the spiral arms reveal their true shapes. The inner regions, once obscured, shine with clarity. Infrared light shows the density of dust, the flow of warm gas, and the outlines of regions where stars are just beginning to emerge. The galaxy seems calmer in this view, more unified, as if the infrared glow smooths its sharper contrasts and illuminates a quiet order beneath the complexity. Ultraviolet light, however, tells a different story. Where infrared highlights the dust, ultraviolet reveals the youngest, hottest stars whose intense radiation floods their surroundings. Through ultraviolet eyes, Andromeda's spiral arms light up like blue fire, ignited by clusters of newborn suns. The bright knots scattered along the arms are not evenly spaced, but appear where gas clouds have recently collapsed and ignited. In these glowing pockets, individual stars burn hotter and faster than their calmer neighbors, giving the galaxy a shimmer of restless energy. Ultraviolet exposure transforms Andromeda into a place of youth and renewal, mapping the regions where the galaxy is actively writing its next generation. Radio waves bring an even deeper perspective. They flow unimpeded through dust and gas, revealing the cold hydrogen that stretches across the galaxy in long, diffuse clouds. When radio telescopes trace these clouds, they uncover the skeleton of Andromeda's structure, the framework on which its spiral arms are built. The hydrogen distribution extends far beyond the visible edges, showing that the galaxy's reach is larger than starlight suggests. The radio signals also reveal how gas moves through the disk, swirling gently in the gravitational currents that shape the arms. From this vantage, the galaxy appears like a living organism with circulatory flows spreading through its body, carrying material from one region to another in a slow but continuous exchange. In radio wavelengths, the halo becomes more than empty space. Faint emissions outline gas streams pulled from past mergers and drawn into Andromeda's gravitational field. These streams stretch across distances too large for visible light to trace, yet radio telescopes detect them as soft arcs, remnants of galaxies consumed long ago. Some of these features reach far into the outskirts, marking old collisions like subtle brushstrokes painted across the halo. X-rays reveal the most dramatic aspects of Andromeda's hidden character. They come from places where matter reaches extreme temperatures, from the edges of collapsed stars, from binary systems where a compact remnant pulls gas from a companion, and from supernova remnants still glowing with energy. These X-ray sources speckle the galaxy like sparks, each one a site of intense transformation. Near the core, X-rays rise from clusters of massive stars and from the hot gas swirling in the region influenced by the central black hole. Although the heart of Andromeda is far quieter than an active quasar, it is not completely still. X-ray vision shows a center alive with compact objects, each one radiating fierce light from interactions invisible in ordinary wavelengths. Some of the brightest X-ray sources come from binary systems where a neutron star or white dwarf draws matter from a partner. The gas spirals inward, heating until it glows in high-energy light. These systems blink with periodic rhythms as the compact remnant rotates, and their pulses help astronomers track the movement of matter across enormous distances. They speak of endings and renewals, of stars compressed into forms so dense that their very existence challenges intuition. At ultraviolet wavelengths, shock fronts from earlier supernova shimmer like faint arcs, their expanding shells still energized long after the star itself has vanished. In infrared, the cooling dust around these remnants glows softly, tracing the edges of the blast. In radio, the shock waves carve cavities in the interstellar medium. Each wavelength reveals a different aspect of the same event, turning a single supernova into a symphony of signals that unfold slowly across the spectrum. When all these signals are combined, the galaxy becomes something far richer than the sum of its visible stars. The spiral arms, which seem smooth in optical photographs, appear mottled and textured in infrared and ultraviolet. The halo, which looks faint and still, becomes a place of motion when traced with radio waves. The core, which glows steadily in visible light, flares with X-ray points that mark intense and violent processes. Every wavelength gives Andromeda a different voice. Together, they reveal a galaxy alive in ways the eye alone could never understand. They show heat, motion, collapse, formation, turbulence, and calm. They uncover the oldest remnants and the youngest stars, the coldest clouds and the hottest explosions. They give depth to what might otherwise seem flat, and they show that even in regions where ordinary starlight fades, the galaxy continues to speak. Across the spectrum, Andromeda tells its full story, a tale of quiet growth, hidden storms, and light that travels in many forms, waiting for someone to listen. From the first moment you look toward Andromeda and see only a faint blur in the night sky, you cannot know how many worlds, histories, forces, and quiet revelations drift within that distant glow. Yet, as each layer of the galaxy unfolds, as each wavelength reveals its secrets and each chapter of its formation becomes clearer, the simple blur transforms into something vast and intricate. Andromeda becomes not just a neighboring spiral, but a living archive of cosmic evolution. Every fact, every hidden structure, every strange phenomenon becomes one thread in a tapestry stretching across millions of years. A tapestry woven from collisions and stillness, from the slow pulse of variable stars to the fierce spasm of supernova, from the cold shadows of dust to the blazing heart of the core. By gathering these discoveries and letting them settle together, the galaxy reveals a deeper truth. It is not a single story, but 1,000 quiet ones layered into a single luminous presence. Its scale alone reshapes the mind. The enormous disk, wide enough to engulf our own galaxy in time, arcs outward with spiral arms that twist gently but carry unimaginable mass. Within them lie glowing star-forming regions, dust lanes that hide entire structures, and the faint trails of stars drawn from galaxies that wandered too near. When the eye first explores the structure, it sees beauty. When the mind lingers, It sees history, written in light and shadow. The double nucleus at the center hints at turbulence and past mergers, a reminder that even a galaxy's core can hold secrets within secrets. Around that core, stars move in loops shaped by forces both visible and hidden, tracing the contours of a gravity deeper than the luminous mass suggests. The oldest stars in Andromeda carry whispers of the early universe. Low in heavy elements, they shine with a softer, more ancient tone, holding compositions forged before the cosmos had time to enrich itself. These stars drift in the halo, far from the disk, surrounded by clusters so old they feel like fossils suspended in space. Their presence reveals the galaxy's earliest beginnings, long before its arms unfurled or its bar took shape. Each one is a window through which we glimpse a time when galaxies were forming from clouds of gas and dark matter, sculpted slowly by gravity's patient hand. Dark matter itself surrounds the galaxy like a silent ocean, invisible, intangible, yet undeniably present. It holds the outskirts in orbit and shapes the speed at which stars rotate. Without it, Andromeda would fly apart, its outer regions escaping into the void. With it, the galaxy's rotation becomes a coherent dance, its arms held together by an unseen halo more massive than everything visible combined. This dark scaffolding supports the luminous forms we see, reminding us that what appears solid and complete is held by something mysterious and unlit. Inside the spiral arms, gas clouds collapse into newborn suns, star-forming regions flicker in bright ultraviolet, and supernova detonate like brief, fierce punctuation marks. These explosions enrich the surrounding space, seeding future stars with the ingredients for planets and life. Their remnants linger in glowing shells and expanding waves, hidden sometimes by dust, revealed brightly in X-rays and radio. Each one marks the death of a massive star, yet each one also marks the beginning of something larger, a cycle of creation woven into the galaxy's constant renewal. In the inner disk and the halo alike, clusters drift with steady grace. Ancient globular families orbit like patient caretakers of memory, their stars tightly bound, their paths shaped by both light and shadow. In contrast, loose open clusters near the arms dissolve into individual stars over time, their members scattering like siblings moving into the wider world. Still farther out, tidal streams from long-dead galaxies wind like silver ribbons, their arcs recording the quiet collisions that built Andromeda's bulk. These streams reveal not violence, but the slow, inevitable merging of structures drawn together across cosmic time. A few stars move differently, ejected at tremendous speeds, flung outward by gravitational encounters so intense that their paths become nearly straight lines into the dark. Hypervelocity stars are solitary travelers, their futures uncertain, their origins marked by drama near the core or within a disrupted cluster. They contrast with the measured rotation of the disk, yet both motions belong equally to the galaxy's nature. One smooth and cohesive, the other sharp and sudden, each telling its own story. The relationship between Andromeda and the Milky Way threads through everything. Two massive spirals drifting toward one another, shaped by the same cosmic web, destined to merge into a new form. The slow approach, invisible in human timescales, becomes more real when seen through radio signals, proper motion studies, and the subtle tug of dark matter halos brushing against each other. One day, the night sky over some distant Earth or its successor world will bloom with Andromeda's expanding glow, the two galaxies weaving into one. But even that epic future unfolds with quiet dignity, like all galactic motion. Slow, elegant, inevitable. Planets form around stars, both young and old, orbiting suns scattered across the arms. Though too distant to detect directly in large numbers, their presence is inferred from clues in stellar motion, dust distribution, and the universal processes that shape planetary systems everywhere. Worlds beyond counting may orbit within Andromeda's expanse, each carrying its own local story, each circling a star pulled gently along the galaxy's spiral flow. Invisible structures also shape Andromeda's life. Magnetic fields thread through its disk and halo, guiding cosmic rays and aligning dust grains. Gas flows rise and fall in great fountains, cooling as they drift into the halo and raining back over millions of years. Variable stars pulse steadily, acting as markers that allow astronomers to map distances in motion. Dust lanes hide entire regions until infrared light reveals them again, reshaping our perception with every new wavelength. Together, these discoveries form a galaxy in full dimension. Not simply a glowing swirl in the night, but a deep and living structure. A place where heat and cold, light and shadow, birth and death all interlace. A place built from encounters, sculpted by gravity, enriched by stars, and sheltered by dark matter. Every detail, taken alone, is astonishing. Yet when woven together, they create something more. A portrait of a galaxy that lives, breathes, grows, and transforms across ages far beyond human measure. Andromeda becomes a reminder of scale, of continuity, of the quiet persistence of matter and light. It shows that even in the cold reach of intergalactic space, beauty forms naturally, shaped by the simplest rules of gravity and time. And as you drift mentally through its arms one last time, letting the facts soften into a single impression, you feel the immensity settle gently around you. The galaxy turns. Stars form. Old remnants drift in the halo. Dust hides and reveals. Light travels across the void. And somewhere within that immeasurable sweep, your own quiet breath rises and falls. A small warmth in a universe of ancient fire.